I still have to confirm with a few speakers and photos as well that we take, okay? So, recording has been initiated, so it's a great pleasure to welcome here Professor Sihem Amer-Yahia on her talk on AI planning for data exploration. And this will be a two-part talk. First part will be on the theoretical part. The second part will be practical. You already received some instructions. Just a few notes about Professor Amer-Yahia. She's a silver medal CNRS research director and deputy director of the Lab of Informatics at the of Grenoble and University Grenoble Alpes. And she works on exploratory data analysis and algorithmic upskilling. She has been at QCRI, Yahoo Research, and of course, she has been very active in the data management community, Sigmund PC Chair, ICD, and so forth. Impact Award, Contributions Award by Sigmund as well, and the BLDB Women's in Database Research Award. Welcome, Sihem.
All right. Kalimera and Ifaristo for inviting me. I'm very happy to be here. It's really exciting because, you know, when I started preparing this, I realized that a lot of what I'm going to be saying that I don't quite understand very well. So it's also an opportunity for me to try and frame a newish research area in particular in the last part of this of the talk. But I did bring in a little bit of like newness at the beginning, so we are, you know, we get an idea of where we're heading. But before that, let me show you where Grenoble is. Since my phone is always set up on walking distance, so I don't know how to go from this point to that point. There must be a way. But so Grenoble is in the southeast of France, at the border with Switzerland and Italy. And it's a very beautiful town. It's a campus city right in the middle of the Alps. And the campus is somewhere up there, top left. There are about 50,000 students, so it's really a widespread campus with several tram stops that go through it. It's very much like an American campus with like a lot of greenery and different departments, obviously. Okay, the place where I work, that's a library at the top, and the bottom is our lab. It's about a 500 people lab, half of which are permanent staff. The other half are students and admins, and two of my students are here, so feel free to talk to them. All right, so this is the outline of my talk. So I'm going to first introduce exploratory data analysis, a little bit about AI planning and what it is and why does it even matter for exploratory data analysis. And then we'll go into more details on how to design a markup decision process and choose your reinforcement, your favorite reinforcement learning algorithm for exploratory data analysis. We're going to try it out and finish with a number of open questions. Feel free to interrupt me anytime.
The online audience capture.
They don't see me?
There you are fine. Yeah.
Hello, online audience. So what's exploratory data analysis? So think, you know, of somebody who's like writing an SQL query and knows exactly what they want to get out of the data. They write the SQL query, they're done, they're gone, you know, whatever. They go home and they're happy, okay? Well, what exploratory data analysis is, it's about eliciting more and more information from the data jointly with the user so that the user refines their need on the go. Okay, so think of, I don't know, like you're online and you want to buy something and you don't exactly know, you know, how much you should be paying for something, what are the different features. All right, but let me give you like a more exciting example that was in the context of a project, the European project called iNode that just ended with the Max Planck Institute, astronomers at the Max Planck Institute, who work on data that comes from the Sloan Digital Sky Survey database. The data looks like this. It's a bunch of numerical measures. Each row is a galaxy with a number of features of the galaxies, including redshift and you know, some kind of density of the galaxy and how far it is from planet Earth. These are mainly measures that are spit out by a big observatory. And what we're going to be, what we focused on is about 2.6 million galaxies. with some clean columns or attribute that describe the galaxies. And we focused on 7 out of the about 100 attributes that describe these galaxies, because these are the ones that are mostly used. We spent about a year and a half going through the logs that astronomers have generated. And these logs are SQL queries. By the way, they know how to write SQL better than you and me. I mean, certainly better than me. All right. So within this project, generally what happens is that the observatory generates a bunch of pictures, right? So they take pictures of these galaxies. There is a cool crowdsourcing project called Galaxy Zoo, where people are invited, or workers, crowd workers, are invited to tag or to label a picture by simply comparing it to different shapes out there, okay? So you just say, which shape is the closest. You can imagine that behind this, this generates a lot of data, and then this data serves training, okay, algorithms. This is super important for astronomers because they need to know, the shapes, matter a great deal into characterizing the galaxies that are being observed. So in fact, it helped the Galaxy Zoo project classify galaxies into about 170 galaxy types, depending on their shapes. Okay, so super cool project. You can play with it. You can go online. Galaxy Zoo evolves, and you feel like you're doing something for science. So in fact, in practice, what happens is that the astronomers spend hours and hours writing SQL queries. By the way, if you're looking for SQL queries to play with, there are like a ton of them on the SDSS website. Okay. So these SQL queries, are generally range queries, right? Because we saw the observations are numerical. And, if you're talking about distance from planet Earth, it doesn't matter that you're at this point or this point, seen from planet Earth. So it's generally, ranges that matter. And in fact, there is an anecdote that led into a discovery where some people who were on Galaxy Zoo landed on pictures like this one, okay? These are very rare. This kind of galaxy, this set of galaxies are very rare. They got they got labeled by crowd workers. What the astronomers did is that based on that, they they went, all right, wow, looks interesting. Let me see, are there any other galaxies out there that look like it, okay? So what they've started doing is some projections in the space based on those descriptions, right, those attributes. And all of that led to kind of a lot of time, a lot of work, until they wrote a SQL query, right? And so, in fact, they do this all the time, right? They take some of the data that's been labeled by crowd workers on Galaxy Zoo, and they're like, can I find, similar data that kind of, am I about to discover a new galaxy, okay? So by the way, the green ones are called green pea galaxies. There are also blueberry galaxies, and there are many others, all right? So look at...
I just wanted to ask, how many dimensions, because it's also of interest in AI with the vector databases and all these multiple, is this like highly dimensional?
The data that we focused on, at least the Max Planck Institute of Astronomy, they focused mainly on 7 attributes. 7 attributes, the ones I showed earlier, but the galaxies have many more, right? About 100 of them. Yeah. All right, so that was one anecdote. Keep it in mind. All right, we'll come back to it. Now, let me introduce what AI planning is. In fact, AI planning is a long-standing area in AI that deals with sequential decision-making. And in fact, reinforcement learning is kind of one sub-area there. It's sort of it's a set of algorithms that implement a certain logic of online decision-making. There are many industrial applications in AI planning, and I put a link there so you get a bit more information about it. And in fact, the AI planning itself is something that there's a lot of software. There are there's some research that goes on, but in fact, the area faces a lot of challenges in becoming an actual research area dedicated to a particular set of tasks, and we'll get back to this. So AI planning is designed to solve tasks of finding a procedural course of action, meaning a series of tasks that you need to be. Think of a robot traversing a maze. Okay, a robot going up, down, right, and left, and the idea of this area of research is to have a declarative description of a system with a goal, right? the particular target goal, and then an optimization that sort of generates a sequence of tasks to take to get somewhere. Okay, are you starting to draw a parallel with navigating in the galaxy space? Maybe. Generally, AI planning is not so much data-driven, it is task-driven, okay? But since we're data management people, we think of things as data, okay? So I'll get back to this connection between the two. All right, so AI planning is about, defining a number of states, a desired goal or goals, a possible set of actions. I want my robot to go from point A to point B, or I want to learn to play a game, okay? Which finite set of actions. A goal is to, score some at some game, but that's sort of the idea. And the behind it is the idea of synthesizing a plan, which is a sequence of states and a sequence of actions to take so that you're satisfying a goal. Okay? In terms of goal, think of it as you're either you have a final state to reach. Okay, you found something and you're done. You found green peas. Okay, you're happy, or your goal is being satisfied as an incremental, right? You're collecting things on the go. For instance, a robot traversing a maze and collecting gold. Okay. So just to give you kind of a high-level reference architecture, in AI planning, the idea is like you want to state the problem declaratively, or you want to run some kind of planner that solves your problem, generate a model, and then reuse this model in the future. Okay, so the idea is that if we understand the mechanics of traversing in a space, right, that is what the model is going to reflect, and in the future it can be reproduced. Hence the need to kind of train a model to go through a number of states of interest. All right, very kind of high-level stuff, but I wanted to just like situate things and give you also an introduction to agentic AI planning, so that we can go back, to dealing with data and then come back to drawing a connection between the two. Now, there is AI planning and then there is agentic AI planning. So the difference, like in 2 words, the difference is that your actions, right, are executed by AI agents, right? The difference between AI planning and agentic AI planning. So basically, this is like really a big area right now, and in particular in industry, and where the idea is that you're coordinating between multiple agents to execute a complex tasks. For instance, making a sale, planning a trip, booking a vacation, and so on and so forth, right? So again, all of this is sort of in the same space of online decision making, where you want to coordinate between different actions. These actions could be either taken by agents or taken by an algorithm, right, that you have written, or taken by a tool. And so given a user task, the goal is to identify a group of agents capable of executing a task in multiple steps or multiple states. These are 2 areas that have evolved historically very, very differently. Okay, the AI planning sort of space with especially the latest agentic AI planning, and the kind of reinforcement learning space. So to give you an idea of the evolution, it doesn't really matter what's, the first column doesn't really matter. The second column is about training a model, right? Simply you have some supervised, machine learning, you're training a model. Generally, the models are used for prediction or classification. And then, the advent of generative AI, where you're prompting a pre-trained model that is generally pre-trained like a reinforcement learning policy or strategy, and mostly used to generate text, images, and videos. And now, more recently, there is the agentic AI, where the notion of planning or the plan is introduced as a way of directing how the agents are going to interact with each other, eventually looping back to revisiting the plan according to what has been observed. Okay, a lot of these things are going to be in some future work discussion, whether there is a memory, whether it's integrated with an outside system or an enterprise system, and then what kind of data is being manipulated by these agents, right? And how do you trigger the feedback loop? Okay, so high-level picture, simply and trying to situate in historically where agentic AI appears. All right. Now, this kind of thing is used in very much. There are so many tools out there that allow you to instruct an agent, an orchestrator, basically, to coordinate between a bunch of agents to execute a number of tasks. Okay, so or subtasks. So for instance, here, what we want the user need or the user query that instructs the orchestrator is going to generate want to generate a tailored email campaign to achieve some amount of sales in 1 month. And then where are the products, right? Where should the agent go and get the product? Maybe you want to connect that to a CRM system, so an enterprise system for customer names, email addresses, and demographic details. So this is kind of the high-level prompt that an orchestrator agent may get, and that's a sort of the high-level task. Now this task gets decomposed either automatically or by hand, right? So pre-specified by users into a number of subtasks, right? So task decomposition, right? Reasoning over a task and decompose it into multiple subtasks can be either automatic or done by hand. And you can see there's a number of subtasks here. I'm not going to go through every one of them. And then there is the question of, at what point we're going to be adding more tasks or more actions, right? If you want to talk in terms of Markov decision processes, and what happens? What are the kind of the non-functional capabilities that are to be deployed to achieve such a task? I know this sounds kind of a little maybe high level, but we're going to go into the details. But I simply want to draw this parallel between agentic AI and online sequential decision making, with some of the steps such as task decomposition, memory management, adaptation, right, loop and generation of tasks, and eventually outside data integration is these are one of the main dimensions that need to be considered in automating agentic AI planning. All right? Okay. Yes.
For the reasoning part, is it the same as chain of thoughts?
Could be done with chain of thought, yeah, or tree of thought, or I think I mentioned it at some point, yeah. Okay. All right, so just to dive a little bit into some of these elements, and then before I take another step back. So the first component of agentic AI planning, well, these are the main dimensions of interest, is an orchestrator or a supervisor that is capable of decomposing tasks into a subtask, or at least understanding that there exists a number of subtasks that need to be coordinated or orchestrated. All right. And these subtasks can be done by some specialized agents. Think of it as planning, even if, you want to talk in terms of data management terms, it really is, a query plan, right? And so what happens here is that mostly for task decomposition, we're doing prompting today, okay? There's some work that sort of, prompting or some advanced kind of prompting, but generally this is what's happening. And so in general, if we are doing it on the fly, it's runtime calls, and which basically may hinder the execution time. Okay. The second step, which is about monitoring the environment or monitoring the execution and coordination between the different agents. There is a number of systems out there. I'm mentioning some of them, and there'll be more information about them later. And then there is the question of how much we know about the context. Is there any kind of memory management that is passed along in the execution? By the way, the very first occurrences of these systems didn't have any memory management. Each agent was like starting from scratch. But most recently, people are talking about using vector databases, in particular with RAG, okay, vector databases to pass on knowledge in an execution. Okay, so this is where you need to situate yourself. Some of the most the new platforms are the Google MCP platform that uses Claude, and then more recently the agent-to-agent platform. Okay, what we're going to be using in our hands-on, right, is LangGraph.
So MCP is not for decomposition, it's just for coordination of the agent.
It's for coordination, exactly. And that's why I want to describe more this collection of tools, okay? So this collection of tools, you look up LangChain, you're gonna find references to LangGraph, you're going to find references to LangFlow, and you're gonna find references to LangSmith, okay? So the very first occurrence of these things was LangChain, okay? And then LangGraph on top of it, and now and then LangSmith appeared, and then LangFlow, okay? So what are these things, right? These are environments, so LangChain is really the backbone. Okay, so if you want to first, if you have a task in mind and you want to try it out, which is what we're going to be doing in the hands-on, I hope, you're going to be using LangChain as the backbone. And LangChain is basically an open source environment where we can define multiple tasks and integrate any language model, right? So we can throw in, for instance, any language model there. I think I specified Llama 3.1 in the hands-on, but you can actually replace it and use another one, okay? It does some prompt management in the sense that, we're going to be doing is each one of the tools, each one of the agents is going to be prompted in some way. So that's in the code, it's going to be written in the code and say, this is how I'm going to be prompted. Of course, the orchestrator gets the general task, the end-to-end goal, right? And then individual tools are instructed to be highly specialized. You could be using like the biggest language model there, but it is instructed to remain specific to the task that it's given to do, or the subtask that it's given to do. And then it enables sort of the chaining of tasks and some level of memory management, which is usually generally, and in our hands-on, it's going to be passing on a file, right? That's going to contain all the stuff that is generated along the way. Then you find the LangGraph, and LangGraph, we're going to be using it too. LangGraph, you can think of it as a graph, or as a graph model, right? Where each node is an agent, right? Edges between them are passing information, right? Eventually, this information can be the memory. In fact, it's a global memory. Can be can be implemented as a file, global file. It contains this information, and then LangChain is what enables sort of this coordination. Okay. And by the way, an orchestrator in this context is going to have some freedom of invoking agents in any order it wants to invoke them. Then, what LangGraph enables to do is to constrain the graph. For instance, you tell the orchestrator, well, you are an orchestrator, and the specialized agents that do subtasks, right, are agents that can only talk to you. They cannot talk to each other, or they can talk to each other, all right? So you can imagine these different graph structures, right, that are either star-shaped, where everything has to pass through the orchestrator. This is the basic one, the one that we have implemented in the hands-on. But there may be other graph structures where some specialized agents will talk to each other. Okay, so that's what LangGraph is for, is to specify the graph, the stopping condition, and all those things. Then you've got LangFlow. It's more for visual design, and this came out after I put together the hands-on. So we don't have LangFlow. So those of you who are really quick maybe can plug in some LangFlow. And LangSmith is more for monitoring, okay? Like the number of tokens that were used, the cost, and all that. All right. So this is the space that we're going to be using for the hands-on. Okay. So now let's go back to like real stuff. Any questions so far?
For the graph, what are the nodes? I didn't get.
Yeah. So in the graph of LangGraph, the nodes are the individual cause agents or specialized agents. Okay. Okay. I'm getting ahead of myself here, but the application we're going to be we have in the hands-on is going to look for products, right? In some Amazon products, okay? And the orchestrator is getting a prompt that characterizes the products we're looking for. We're going to look at the prompt and how it looks like, and then individual agents, right? They're tools that do very specific things. One is going to extract sentiment from the reviews, right? One is going to compare product based on similarity, attribute similarity, and so on and so forth. Okay. So the interesting thing is that you just tell the orchestrator, hey, the graph you're able to instantiate is this one. Okay. But you can call these different agents in any order you want. So people are using that a lot to generate plans, right? And then studying those plans. Okay, now let's go back to reinforcement learning, for exploratory data analysis. This is an area that's been quite hot in the last few years with the number of groups in different places in the world that work on it. And I shamelessly summarize work that I have done. I did try to summarize other work and then it sort of blew up. So I'm just going to talk about some of the stuff that we've done. So, all right. So, as I said, the work was in the context of exploring galaxies. And to do that, we're going to be thinking of the space through which we're going to be navigating as a set of states or galaxies that are described with interesting attribute values. You can see that the values are ranges, right? Defined over by binning the attributes generated in SDSS, all right? So, and each one of these, and this is just really just a uniform sampling of some of the pictures of the galaxies that are in each set. Okay, so my state is going to be this, and this is really how the astronomers look at it, right? They don't look at individual galaxies, they look at a number of combination of attributes. This is a conjunction. These are like item sets in data mining, right? So you can read this as being a conjunction of predicates, right? So all of these here, they satisfy this value and this value and this value and this value, all right? So this is what our space is going to look like. And this is exactly what I just said. And when I said we spent some time examining the logs, right, of those SQL queries, we thought, okay, to help these astronomers, go faster in their exploration, we're going to encapsulate the SQL queries in the most common operations that they're doing over these item sets. Okay, now think of these item sets as organized in a lattice. Okay, so what's a lattice? It's a graph where a node may have multiple parents, multiple children. The parents of a node are obtained by dropping one of the predicates. Okay, you drop one of the predicates, you end up with a superset. Okay, you add another predicate, you end up with a subset. Okay, these things they do all the time in their SQL queries, right? They're adding, they're specializing, they're getting rid of some predicates, and they're like, okay, wait, am I getting like closer to planet Earth or farther away from planet Earth? This is the kind of reasoning that they had. Okay, when they're exploring the data, they have some idea in mind of what they're looking for, which is of course, we don't know these things. We know a little bit of these things. These are the target items, right? Blueberries or green peas or yellow edge galaxies, a number of them, right? And the way they're going to be navigating in this space by writing and rewriting their SQL queries, this is an important thing, so please pay attention, is by either jumping in the space. So they will like look at an item set and they're like, is there another item set that shares similar attribute values? Right? So if you think of it, in your lattice structure, it doesn't have that, it doesn't have an edge like that. It has only like superset and subset, right? So in fact, sometimes they're jumping. It's almost like a random walk, but they're directed in a semantics way. Does there exist another set of galaxies that have kind of similar redshift? Okay, so they're either jumping, right? Or they're going kind of step by step, right? They may be like looking for supersets, subsets, drilling down and rolling up, okay? Okay, and sometimes they're just staying within like this tiny little space, they're just like drilling down, or right. So these are just this is important because it sort of like encapsulates what they're doing into a number of operators. Okay, so what we ended up doing is we took the work that people have been doing in data exploration, which is generally the first two operators. Okay, so if you think of your set where you are as the solid circle. Okay, what you're doing by rewriting, what they were doing by rewriting their SQL queries is either to look for subsets, clean subset, right? That you can define, by the way, this is depicted more as a group by, right? This is a group by query within a set. But it can also be a kind of a finding overlapping subsets, like solving an optimization problem or like a set cover kind of problem. But this is very common, because they want to know, out of all the galaxies they're examining, all the sub-galaxies, if it can be broken down by density. The second thing, the second kind of operator is to find the smallest containing superset. I drop one predicate, I drop the other predicate, I drop the other predicate. Very important, okay? These are very common in data exploration, right? Drilling down, stylized drill down and stylized roll up, okay? And then two other operators, right, are done very, very frequently. One is to look at neighboring sets. What is that? You're relaxing one of the attributes, right? Why are they neighboring? They're neighboring in the lattice. They're like siblings in a lattice, okay? So basically, you know, this is like the one I mentioned earlier, which is given an input set, I want to return the galaxies, find galaxies that are a little bit farther, a little bit closer to planet Earth, okay? And finally, this thing that we called bi-analytics or bi-distribution is the one I was telling you earlier about, that is jumping in the space, guided by similarity in some data distribution. Of course, these can be solved this can be solved as an optimization problem, right? This can be in SQL, this is more or less easy to do. This is also easy to do. And then this is also an optimization problem. Or if it's stylized like we did it, you drop some predicates. This is how you find the next ones, okay? Now think of them, you know, producing logs and logs of SQL queries that are doing this, right? So we thought, can we make their life easier? Can we automate this process? This is an online decision-making process where we have at our disposal data manipulation operators, okay? Hoping, of course, that we'll be learning navigation policies that mimic the mental process of finding green pea galaxies, okay? Once I have learned those policies, I have the hope of being able to reuse them. Got it? So this is it. Now, to get there, okay, before we talk about the algorithmics of things, there is this space there is this way of formalizing this space as a Markov decision process. So what's an MDP, Markov decision process, is a set of states, of actions, a reward function, and an environment, okay? And transition probabilities between your actions, all right? This is not the algorithm. This is the declarative way, right, of specifying your space. So how do I specify my space? I have to think about what are my states. In our case, the states are, what are the states? The states are sets of item sets that I'm manipulating right now, okay? I'm starting to be doubtful about my, either I should doubt about myself, that I'm not very clear. All right, so what is going on? Each SQL query gives, returns a set of item sets of galaxies, right? So this constitutes my current state, right? And then I'm like, okay, what should I be doing next, you know, to find my green peas? So I apply some SQL or some operator, right? And then it's going to generate the next state. Okay, all right. So so my states are at least, right, the set of item sets, right? Of course, they can have much more than that. The operator that's been used to generate them, I don't know, the size of the item sets. Think of that as a feature vector. Okay, that's how states are usually implemented or represented. What are my actions? My actions are these. That's all I'm allowing my agent to do, okay? And in fact, I can even reduce the agent's expressive power. I can say, all my agent is able to do is to go up and down in the lattice. The agent is not able to jump in space, okay? I'll show you how this affects the ability of the agent to navigate in space, all right? So think of this, right, as a kind of a library of operators, or, you know, really what it does, it determines, you know, how powerful the agent is in navigating in the data space. The data space being a set of item sets, all right? Okay.
But Sihem, maybe you mentioned and I missed it, but what would be a typical agentic workflow for this agent? These are the operators, of course, but just say the basic scenario of, because maybe you have like hundreds of scenarios, each scientist defines its own scenarios. They just want to have a basic set of operators to compile together agentic plans. But what would be a very typical scenario, like capture the pictures and then find me, you know, I mean,
subsets, find me supersets. These are like the super basic ones.
so just a single invocation of an operator rather than several of them.
It's a single invocation at a time. Yeah, whether there are compound invocations is something that you can use.
So it's not like a compound.
Right now, it's a single invocation at a time. That's atomic, right? But yeah, you're right. It may be a compounded. I'll tell you why. Because think of it, you know, like the lattice is huge, right? And to get from point A to point B somewhere in the lattice, right? If you only have at your disposal, right, a drill down and roll up, you keep just going up and up, down, 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 right? That's like your way of getting there, right? Because of the way the item sets are defined. If what you're doing is navigating on Amazon, for instance, products, what are your actions, right? You cannot do much. You cannot take it. And Amazon does not allow you to take an item and find similar items. Well, they have people who bought this also bought that. That's as much as you can get in terms of action, right? Basically, you can think of it as
it's a strategy, basically.
It's an application. It's also dictated by the application, right? If you take in Amazon, you cannot like, how many times, you know, not I, but I'd say my husband, he loves to spend time looking at, you know, what people think of things and, right? And he's like, oh, this guy, I think I saw his review, right? We were looking for a hotel in Paphos, right? And he's like, I think I saw his name for some hotel. He seems to be having the same review. I need to find his reviews elsewhere. And I'm like, you don't have a way of finding his reviews elsewhere. You're gonna have to go back to each item, to each hotel and look at this guy, look for this guy, right? But you can imagine, right? The system where you have that expressive power. Right? So that's, yeah. So, you know, the decision of the operators is a design question. All right, so let's move on. So, and then there's, you know, like, how do we let the agent navigate in the space, which is what we're saying. Do we let the agent jump in the space, right, in some semantic way? And then what is my reward, right? If I am to train an agent, right, to put together a bunch of operators to navigate in a space, given maybe a target, a golden set, right? How do I define my reward, right? Do I define my reward in such a way that it finds similar items, different items, right? Does it get rewarded for that, right? Does it get rewarded for just finding the actual green piece? It's going to take a long time. Or do I allow my agent to venture in the space, right? And we'll get back to this in a second. And then there is reinforcement learning is actually an implementation of this of Markov decision processes, right? It's an implementation choice. It's an algorithmic way of implementing Markov decision processes, and there are many, many, many different algorithms out there. And the GIM environment allows you to plug in different algorithms, right, from an implementation perspective. Okay, so an MDP is an agent, is basically defining an agent, a set of states, a set of actions, right? A reward that you may get from applying an action that takes you from state S to state S prime. And what an implementation of and an environment that you're interacting with, an implementation of this is simply a training of the agent, right? To generate the best policy, the policy that maximizes the reward, right? Generally the cumulative reward of applying individual actions to transition from state S to state S prime. Hence the need for the operators, if we're doing data actions, right? It's not like navigating in a maze, right? You go up, down, right, left. Data actions has the need for because we're composing the operators must be closed under the same data model, right? They need to be talking to each other, meaning that, you know, I cannot be running an operator that's generating apples and then an operator that needs oranges as input, right? Hence the item sets data model, right? All the operators we have are closed under the item sets data model. They produce item sets, they take an item set as input, and then they produce K item sets, then the next one is going to choose an item set, produces K item sets, and so on and so forth. Got it? Okay, so this is how it was defined. Now, this is simply to give you a big picture of the variety of reinforcement learning algorithms out there. Some are model-free, some are model-based. The most used ones are model-free ones, where you basically learning your policy or generating your best policy by navigating in the space. And there are many, many algorithms. The most common ones that we can find are based on either Q learning, so you're learning a transition function, Q values, between different states by applying, think of it as a matrix, right? By applying an action to go from one state to another, that gives you a value that corresponds to your reward, okay? And then it's a question of finding a sequence of actions that maximize the discounted cumulative reward. Why is it discounted? Because obviously, if you're not discounting, the longer the policy, the higher the reward. So it's going to go for the longest policy. But what you want is to encourage the agent to pick the best actions from the start, right? And not sort of like linger and linger and linger. Okay. I think I've put in a, so there is, this one is one of the most common one. And one of the most proficient one is the actor critic architecture, where you have a number, sort of, it's like a two-level architecture where you have what they call a worker and a critic, and the worker and critic, they collaborate to update the reward. You know, there is a notion of advantage that sort of incrementally updates the reward, just a two-tier architecture, but there may be more than multiple worker critics that work in parallel to update the reward. Okay, so these are all basically implementations of that. There is a deep Q learning variant where you're actually using, you know, deep learning to learn the rewards, right, or the Q values. But you know, there's a whole slew of them, and that's not the point. I did put some summary of model-free and model-based algorithms, just for the purpose of you having them here, but I'm not gonna read out what's there. So let's start with the first application of this. Okay? The first application is navigating in galaxies. The second one is summarizing galaxies and music on Spotify. And the last one is navigating in Amazon products. And that's what you're gonna be doing in the hands-on session. Any questions so far?
Question, what? For the second part, why do we need the reinforcement learning part? Couldn't it be one, you know, simple search, let's say A* search that has an objective function, and that, I mean, I'm just trying to understand the argument for a reinforcement learning.
A couple of things. One is reusability. So you're learning a policy that then once you have learned it, you don't need to train it again. Okay, so you just like, and then the second thing is this effect of sort of iterative reinjection of reward. In other terms, when you are at stage S, right, you don't necessarily obviously know, since it's kind of a greedy way of collecting the reward, you don't necessarily know what will lead you to a better choice. So in fact, the way it's generally is the way the policies are learned is sort of in this iterative fashion until the reward stabilizes. Okay, so it's not just a forward. Absolutely, it's not just a forward-looking algorithm. Yeah, but I'm sure. I mean, I don't know if there are any comparisons that have been done, but I'm sure, you know, there are applications where there's no need for such kind of a complex.
Yeah, because there are evolutionary algorithms, for instance, that do, you know, conflicting objectives, multi-objective. You mentioned it also.
Also, I mean, these algorithms, they're generally they're online, right? The one you mentioned, right? So you have your need, you kind of run your thing, and so you generally are trying to be, you know, sub-second, and it's heuristic based. Everything is heuristic anyways. Here you can afford to train, right? And it takes hours, and yeah. So, all right, let's start with this example. Okay. So what is this one? So this is a piece of work we did. That was sort of a bit of a serendipitous thing, right? So I was giving this talk about, you know, astronomers and SQL queries and what are we going to be doing with that? And yes, we want to use reinforcement learning at the time. And I'm like, okay, here's my agent, here's blah. my reward should be that I will be training an agent based on their ability to find the green pea galaxies, because there are so few of them that, I should be able to train an agent to find them. Okay. And then somebody in the audience said, but there is this thing that they use in learning to play a game where you're training an agent, basically, right? To play familiar strikes, but also to sometimes be curious, okay? And try some other strikes, because maybe the agent could be, could find sort of a strategy of winning, right, the game that, would benefit sort of its overall score. And so I thought, maybe we could try something like this, right? So with Brit and Aurelia, we thought, well, let's define a reward that is a linear, weighted linear combination between a notion of familiarity. So I have a target set, big T. Think of it as green peas, for instance, right? So my target set can either be, you saw those 3 pictures I showed you earlier with the yellow stars, right? It can be like completely scattered in the space, or it can be, there's a little bit here, a little bit there, or it can be like super focused in the space. The target that I don't know that I'm looking for, okay? So given the target set, right, for the training, I'm going to be defining my MDP and giving it this reward function. That is a reward function where the agent is going to be encouraged to pick one of the 4 operators that we have. Remember, the 4 operators that gives it some familiarity, which is simply, does that operator yield K item sets that maximize overlap with the target set? Okay? Basically, does that operator lend me on a set of item sets that have anything in common with my target? So that's the familiarity. Okay, you can see it as Jacquard, or doesn't matter. Curiosity is basically simply, you see, it's not even dependent on the target set. It's encouraging the agent to venture in the space and find a new set it has never seen in the past. Be curious, jump, find something, right? So generally, curiosity encourages the agent to pick the by distribution, remember, and the by neighbors, right? Not so much the superset and subsets, but sometimes it does, right? So that's what the reward was in our MDP.
So the target is the input set?
The target is the input set. And what you're learning is not, of course, you're trained to find that, right? But what you're actually learning at the end is to find sets that are scattered in the same way as that. Meaning that at inference time, once we've trained an agent with this target, that is the input set, we can start it from any other space, point in space, any other item set, and it's going to find sets that are scattered in the space in the same way as big T.
Similarity like similarity?
Absolutely. So let me try and find another analogy. Let's say your target set, right, is looking for product electronics, right, like the cameras in the space, okay, and it could start from anywhere. You could even start from books, right? And what you want your agent to do is to lead you to a set that is connected through user reviews in the same way as cameras are. So same thing for galaxies, right? What matters to the astronomers is not to find things that have been found before, it's like, okay, green peas have been found, so no. They want to find galaxies that we can reach through a set of actions that are connected between, where the process, right, of getting, the process of getting to those galaxies is similar to getting to green peas.
Yeah, I'm thinking of the implementation of this, how to measure this familiarity as like the similarity between 2 vectors.
Yes. No. The way we implemented it here is, I think it's a Jacquard. It's basically each operator generates a set of item sets, right? We simply compute the intersection between those item sets and our target divided by the size, the size intersection divided by the size of the union.
Intersection over union.
Question, yeah.
So this problem can be reduced to multi-armed bandit?
Okay, this is stateful. Multi-armed bandit is stateless. okay? You can define exactly the same thing as a multi-arm bandit, where your arms are actions, they're our operators. Your reward is the same, except that you don't have at the end, right? I mean, it's all online, right? You're pulling your arms and you're being encouraged doing this or that, right? But you don't have a policy that you have learned, right? And you can store and reason over it. Question?
This is still reasoning over known unknown.
Yes, absolutely. Yes, but what you know is the scattering in the space of this target set. Okay.
You also have some sort of like these hoppings that you mentioned.
Sorry?
So you also mentioned that there are some hoppings that.
Sure. Yeah.
Is that
That's
for some of the like out of distribution?
No, this is actually this is something that we introduced by looking at how in an exploration session on SDSS, what happens between two consecutive rewrite of the same SQL query, right? So basically what they do is that they would write the SQL query, they look at it, they look at the results, and then they're like, I'm gonna rewrite it, right? In many, many cases, rewriting the query corresponds to one of these operations. And then sometimes it ended up being one of these. So we're kind of trying to mimic what they're doing. Other question?
On this slide, how do you define the number of items?
Okay, so this is really super stylized. So this is, you have a set, right? So let's go back to one of our sets here, okay? And let's say Petrorad is not there, okay? The set is defined by a conjunction of 1, 2, 3 predicates. And the drill down is a group by Petrorad. That's it. And it's gonna give you distinct sets, as many as there are distinct intervals for Petrorad. Very simple. In this case. Other questions?
Yes, about curiosity, how is it calculated?
It's simply encouraging the agent to generate states that it hasn't seen before. When you find a state that you haven't seen before, you get a 1, otherwise you get a 0.
Okay.
Seen before meaning the item sets that that state contains. Where am I going? The item sets that that state contains and none of the item sets that you have encountered.
Okay, but but isn't the whole target the output data set is familiarity plus curiosity?
We'll see.
Okay.
Oh yeah, this we already. I think this we said it over and over again. Yeah, question.
Is this thematic akin to exploration versus exploitation?
Yeah. It's a kind of a very specific way of defining it, and more of a data. It's a data way of defining it, right? Because one is overlap with the target set, and the other one is finding states that I haven't seen. But it is like exploit, explore, right?
My question: what is EI there and R delta and beta?
It's the action. EI is one of the actions that you are applying. Yeah, I should have written AI. Yeah.
R delta and beta predefined, chosen beforehand.
The training set. Yeah, it's big T. Is that what you were saying? Was that the question?
The beta and the.
We've looked at different beta, and you'll see.
So beta and delta is the balance between exploration and exploit.
Yes, absolutely. Yeah. So we're not doing, like epsilon greedy, in MAP, but we're basically controlling those weights. Okay. All right. So what did we do? We used A3C to implement this. We trained a bunch of agents, obviously with different weights of curiosity and familiarity, and with different target sets. Okay. And then we ended up with a bunch of pipelines, right, that users could choose from online, right, in the interface. So by the way, Dora has the code is available. I mean, everything is there. Okay, so you can download it and play with it. And then we provided users with 3 modes. One is user picks from the pre-trained policies, one of the pre-trained policies, or user composes their own policy by just going in a stepwise fashion, or user is in a semi-guided way where launches a policy and says, sometimes stop, I want to put in my own operator. I'm not happy with the operator you have, so I undo the previous step and then I'm going to try something else. Okay? It was important. The semi-guided way, which I'm not going to go into to many details, was very important for astronomers because they wanted to retain some agency. Okay? And they're like, yeah, automation is great, but we also want to intervene. Okay? So that's the one that they ended up, really using. All right, so let me tell you a little bit about the experiments. You're asking about weights and how we set up things and so on. So let me tell you about some of the results. So we've got here, so for training, right? For instance, you could sample galaxies out of a number of galaxies, or you can choose, it depends on their distribution in the space. What I'm going to show you is the result of sampling, uniform sampling of 100 galaxies in the space. So you can imagine that this is a picture where you're like really going, remember the yellow star picture, right? So there's kind of like a uniform sampling of 100 galaxies, and this from the 169 galaxy types, right? This becomes our training set, and then we're training the agents. So what are the experimental settings? There's one case where the only operators that we give the agents are a drill down or roll up. The only thing they're able to do, right, is they have a set, they're only able to look at subsets or supersets, okay? Because we wanted to kind of see, like, really, does it make a difference to have more expressive power in terms of navigating in the space, all right? And then we've got the all operator version. We trained 5 agents. I'm reporting the results of training 5 agents for 100 hours. For about 1,700 episodes, each containing 250 operations. I'm laughing because obviously you train like thousands of things. And we looked at the reward evolution and, did it make sense to use these operators or not? And finally, these are the variants of the agents, right? So familiarity only, which is the most commonly used up to that point, right? That's what people do. They're like, okay, I have a target set. Can I train an agent to find the target set? No notion of curiosity or nothing, right? So what are the operators that the agent is going to learn? Then we did curiosity only, why not? Okay. And then combinations of familiarity and curiosity with different weights, okay? This was to your question about the explore exploit with the weighting mechanism, okay? So in one case, we're only exploiting with familiarity, curiosity, we're only exploring, and then we're kind of weighing these two reward components.
Only equivalent to random, just random.
Really a random, it's not so random because the only way you can be curious, you can move from one state to the next is by applying an action, and our actions are the operators, right? So in fact, what happens is that it generally doesn't do by superset, by subset, or by passive. It does the other ones, okay?
One more question. In your architecture earlier, did you talk about some deterministic policy that maps, these reinforcement?
It's deterministic.
It is,
yeah.
You have specifically MDB?
Yeah. Where the probability of transitioning from state S to S prime is through the application of an action A, and you always, get the same results because it's a data operation that we're doing. Right.
So in the line FAMO for familiarity only,
yeah,
this mimic existing data exploitation should be right.
Yeah. But I mean, this term in the space of data exploration, like exploratory data analysis, right? It's the research area of data exploration, but the behavior, yeah, it's an exploitation. Yeah. I mean, this term exploration is from the data management community, and the term exploration for curiosity is from the machine learning. But good point. Okay, so let's look at some of these graphs. So basically, each one of these graphs is showing you the episodes, right? The training, right? And the rewards that are accumulated. And I'm breaking it down into the curiosity reward. First, I'm going to show you the curiosity reward. And are we able to encourage the agent? Is the agent able to be curious, right? If all we're giving that agent are the traditional operators, right? The roll up and drill down, which I think it's answering some of the concerns that were there. And we can see here that you know, the curiosity reward is kind of hard to obtain with traditional operators. You know, it's, where is my cursor? Somewhere here. So bottom left graph shows us that the curiosity is like pretty is quite low, while when we're increasing the expressive power of the agent by giving it more operators jumping in the space, it's going to yield higher curiosity rewards, regardless of the reward function. Got it? Okay. I mean, obviously, the familiarity only agent, right, has quite low curiosity reward, and it also does not really stabilize. The one that does best is the red one that sort of encourages curiosity. Okay, I mean, this is kind of a sanity check showing that the agent training is kind of complying more or less with what we're expecting it to do. And just for the sake of vocabulary, curiosity is also referred to as intrinsic reward, and the other one, familiarity, is referred to as extrinsic in the reinforcement learning literature. Other point, yeah. So then you would think, okay, since, you know, I'm encouraging my agent to be curious, why not go with curiosity and just, like, you know, venture in the space until I find something? Well, it turns out that okay, remember when I said our training set was like a sample of 100 galaxies of all the data? So basically we called it like taking a tour of the data, right? Because this is what it's supposed to be mimicking. I saw you, sorry. And so when we're only basically curiosity only, right? If we're encouraging the agent to be curious, right? The bottom one, sorry for the colorblind. I mean, this predates when I was concerned with DEI. Basically, the bottom line, mostly, is a line that encourages curiosity, and it's yielding not so good familiarity rewards. Question? Yeah.
Convergence is guaranteed using only curiosity.
Only curiosity? We actually did, yeah. Let's see. I should have the one that sort of merges the two. Let's check. But intuitively, yeah. Why would it work if all we're doing is encouraging the agent to? I mean, intuitively, right? What's happening is that it's converging because once it's done exploring the states, right? Because, you know, yeah, it's encouraged to pick things that it hasn't seen before. Yeah, and since in the lattice there is a lot of overlap between the data, it tends to really pick the sets that do not overlap, kind of siblings, more or less. I mean, if the notion of sibling exists in a lattice, which doesn't really exist, but you see what I mean, right? People, item sets or nodes whose lowest common ancestor is very high in the tree. That's really what the siblings are. Okay, and so really the best results are obtained with mixed reward agents, which kind of mix up both familiarity and curiosity. And I think it's the one that does 25-75 or 75-25 that does best, you know, if we look. So we're looking at both familiarity and curiosity here. Yeah, I think this merges the two. I don't know if I have a graph that sort of really confounds the two weights. I should have it, but I don't have it. Okay, well, and then what this is showing is simply which agent uses which operators, right? So so the agents that have a mix of rewards, right, both curiosity and familiarity, tend to pick out of all 4 operators, right? Of course, encouraging some operators more than others. The by neighbor operators comes back a lot. Okay, and then what this so both of them are during this is during training. Okay, basically what are the operators that are picked by the agents, and that's in the deployment when we tried it out on a number with different starting points, right? The inference phase. Okay. So you see the question also that was asked here is you can the common practice in reinforcement learning is to capture everything in the state description and in the reward formulation. What we've added here is data manipulation operators, right? And the question of whether the agent is going to choose out of which one of those data manipulation operators the agent is going to be choosing from. So, and we can see that in some cases, right, where the agent is encouraged to being just look for familiarity, right? It naturally going to look only at drill down and roll up because that's where there is the most overlap, right? While in other cases when you want to balance familiarity and curiosity, this is where it's going to use the range of operators that you have. There was a question in the back.
Yeah, I was wondering, like, initially you showed us like some tiny peaks, very long back. Are those kind of corresponding with these graphs?
Yeah, you mean the yellow star pictures, right? Yeah, the yellow star pictures showed the case where, because our training set for this particular experiment, our training set was a uniform sampling of 100 galaxies, right? So really what is happening there is more.
Yeah, and
or
like, does the order really matter? Because kind of shows up here as well.
Does the order of choosing operators matter? Is that what your question is?
So if you go to the final slide that you were showing us, here you see the randomness. There are some peaks and there are some like drops, and those kind of remind me of like the first picture that you showed me.
Yeah.
So I wondered that if you like randomly swap them, would they also reserve somehow?
That's a very good point. So basically what you're telling me is that your RL agent is going to learn a plan, like a query plan, right? Like a series of calls to different operations, different queries, you can see them that way, right? Now, if we can make that persistent, right, and reason over those plans, right, then we can start asking the question of ordering those nodes or reordering them in such a way that, you know, I don't know, we want to optimize some dimension, either performance or even finding the targets. Now, those kind of optimizations, right, they would only make sense, right, if, obviously, if you can apply the switching, right, because it may not be able to, depending on what the operators are, okay, and if you're only using your learning, right, as a way of, I mean, training the agent as a way of generating plans, right? So it's like you say, okay, I'm going to sample a bunch of target sets. I'm going to use that as a way of generating plans, and then I'm going to start reasoning over those plans. Okay, so it's sort of this two-stage thing, right? Today, I mean, as of today, you know, there is these two worlds evolve separately, right? In the sense that I'm given a bunch of plans, can I reason over them, right? Versus can I generate plans out of the reasoning that I have, right? So it's two different things, right?
The question is that since you're learning from data and since you're modeling on that, there is some inherent like epistemic bias there.
Yeah.
So if you're switching them around, then you would account for that. So it's like either ensembling or choosing different samples of the data. And I wonder like if this is relevant.
It depends what you're after. If you're after some empirical heuristic, you know, kind of, as you mentioned, ensembling, then yeah, you can try it out and see. But I think the nature of the work here, you know, resides in the design of the operators, right? And so, you know, it's not the same thing to do that kind of like switching and reasoning over trajectories of a robot in a maze, right? Where it's always the same goal, it's always the same set of states, right? And basically, you know, you're either going left or right, and then you're thinking of it as, how do I ensemble different ways of reaching that same goal? What happens here is that, remember that what's happening is we're transforming data as we go along, right? So ultimately, different orderings of the operators are going to transform data differently. Even if your reward is comparable, but at the end, you may find 500 green pea galaxies, another 500, but they're not the same 500 green pea galaxies. So the ensembling could be something that has as an objective, for instance, to find all or as many as possible of the green peas, right? I don't know if I made myself, yeah? So data transformation is at the heart of these operations, which makes things different. I mean, obviously, we're only sending a reward signal to the agent, but the same reward signal may translate into very different data in the back, right? Okay, Dora. And now I'm going to quickly tell you about EDA for some before telling you about the multi-objective EDA, which I hope I will get through so that we have time for our break and then for our hands-on. Yes.
A question on the last slide where you say the curiosity reward is promoting more use of neighbor-based operator.
Yeah.
While not the distribution one. Why is that so?
It's a good question. I don't know. Requires a bit more, thinking. I don't know. Maybe it's because of the sampling, maybe because the 100 galaxies that we're looking at, like by looking at neighbors, you're more likely to land on a different type of galaxy, okay? Rather than just like going and finding other galaxies that have similar distributions.
Other galaxies with similar distribution also have a high J-value.
Other galaxies with similar distributions might either have a hijacked value or might find galaxy types that are similar to the ones that you're already looking at. And hence you're not finding more targets. Possibly, yeah. I think it requires more investigation. Yeah, I think the conjecture that the by neighbors is encouraged because it finds galaxy types that are different is more likely to be true than the other conjectures that I've just said. Yeah, good point, yeah. But I think the point of that work is also to bring together sort of what's going on at the data level, right? The data types at data level, data transformations, and this formulation of reward that in a way it's kind of a little remote from what's happening on the data. And so bringing those together is something that is still under investigation in a way, right? Open work. And hopefully with the multi-objective EDA, I'm going to tell you a little more about it. And it looks like it's going to eat up on either the break or maybe they're trying it out. We'll see. Just a quick thing on exploratory data analysis for data summarization. Similar settings, okay? We built on Dora. The only difference is, not really the only difference, but one of the main differences is the reward. I'm mentioning this simply to show you that there are many ways of thinking about the specification of the MDP for different purposes. What was the purpose of this work? It was when people do data summarization, that's a very common research topic in the data management community. They're going to look at data and they're like, the best way to summarize these tables, right, is to come up with an algorithm that's going to look at data distributions, right? And then it's going to look at your schema and it's going to look at the column distributions, right? And it's going to characterize the distributions and it's going to come up with a representation of tables that is more compact, okay? And all of this is done in one shot, one algorithm, right? And then we're going to look at the outcome of that, right? So Deeparoy does a lot of that work. Very, very interesting work, okay? What we did here, she's at Duke, by the way. What we did here is we thought, can we think of it as an iterative process? Data summarization is an iterative process, especially when you're dealing with a very large data set like galaxies, right? What's the likelihood of being completely satisfied with a single summary? So what we did is we thought, let's do an iterative process where we generate a series of summaries, right? And compare that with an algorithm that does a one-shot summarization, okay? So what goes into the ingredients of the reward, similar states and so on, what goes into the ingredient of the reward, right, is a notion of uniformity. When you're generating a summary, you want your item sets to be uniform in the sense that each item set kind of represents a summary of data that is alike. You want a certain diversity between the item sets because you want to cover a wide range, right, of data, and you want to encourage some novelty between different steps. Okay, so basically this is what we looked at in the data summarization space, and at the top you can see a highly uniform item set. At the bottom is a non-uniform item set, and we were encouraging summaries that are formed by k item sets, right, that are themselves uniform, but that are very different across each other. There is a certain diversity. And I want each summary at each iteration to be very different from the previous ones, okay? So I wanted just to mention this so you can see that there are many ways of applying this work. I mean, you can even play with it, get Dora's code, and change your reward function and maybe some of the state representations to implement a bunch of applications, right? So this was the data summarization one. We also tried it out in this work against Spotify data. And it was really cool because we could like really see some of the sets. This is one of the item sets of Spotify, and some of the sets were being grouped based on the kind of instruments that are played. How is it music that is loud versus less loud, right? So we ended up like with these summaries of like loudness as being kind of a diversity criteria, or popularity, like the most commonly whatever pop music kind of songs were being clumped together. It was really cool to look at it, to look at the space, because you could see, right, that depending on how obviously all goes into the definition of these uniformity and diversity, right, functions, right? Novelty is simply a novelty of a state, right? Things that I haven't seen in the past. But you can see that iterative data summarization applied to this, right, can yield some, kind of serendipitous summaries, just, for your information. And then there is this last piece, which I wonder if we should, let's start, right? I'll start it now and then see how much of it we're going to go into. I really love this last piece of work because it gets even closer to the data, and it goes kind of still exploits the fact that we are training agents and we can specify reward functions and so on. But you see how much closer it gets to data management. Okay, so the setting of this last piece is the one that we're going to be playing with in our hands-on. And basically the idea is that you want to be able to learn how to navigate in a large space of unstructured data, structured and unstructured content, Amazon reviews for products or IMDb reviews and movies. And so the question is, can we kind of, look at this as again, design our MVP and see if we can come up with an exploration space where we have a bunch of actions that make sense, that reflect how a system like this works, or how people actually think and navigate in a state of reviews and to find products, for instance. Okay, this was work that was done by Behruz, who is actually now at Amazon. It was during his PhD with me.
So their policy will be the chain of thought of a customer when choosing a product?
If you want to call it that way, yes, exactly. So yeah, so here is kind of the motivating example. You're looking for a camera, you kind of more or less know what you're looking for, but not exactly. And so obviously you're going to look at the camera. Oh, okay, so I must have gotten rid of the iteration, but you look at the camera and maybe you're going to look at reviews, and then from those reviews, you may look at other reviews because you want to look from one review to another, right? Maybe there are some overlap in opinion or overlap in some concepts or topics that are covered by the review. And then from that one, potentially, you're going to find a camera, right, that has some of the features that are raised in some of the reviews. Of course, the application itself, the way it's implemented, the website itself, may or not allow you to directly go from one type of object to another, right? That could be kind of a restriction in the implementation of it. But we, as data people, we can think of these as objects being products or reviews. Each object has a set of features, right? And then how are we going from a set of object to another set of objects, right? That's sort of how we looked at it, right? So for instance, here I'm showing you a review. This is on IMDb, and I have a review signature, right, that I can extract. At the time we used Glove, but of course afterward we kind of, and in the implementation that you're going to be playing with, we use the language model to generate a summary. We have the text of the review, the summary, a summary of that text, a set of tags extracted from the reviews, a set of sentiments, a set of topics, a number of things that characterize the review. And all of these are things that is basically a vector, right? A feature vector that can be generated from a review, or for a user, which is basically by putting together all the reviews of that user, or for a product or an item by, again, representing it as a vector of features, okay? And so at the heart of it, right, is this high-level operation. So this is what our action is going to be, of exploring, right? I'm going to use the term exploring, but maybe I may mean exploit, okay? So exploring admits an object, right, which can be either, you know, an item or a review, a space of objects that are items or reviews, and returns a subset of items or reviews. That's it. That's what explore does. And it does that by looking at some kind of relevance, right? Given an object, it's going to find other relevant objects, right? And some notion of quality of the returned set of objects that I mean, that you know, I'll get to or not, but we'll, you know. Anyways, I'm encapsulating everything into a single operator called explore, and it's sort of a polymorphic operator, right? It can take either items or reviews. It generates items or reviews based on some notion of relevance and quality. Don't you think it's the way we think about navigating in the review space and object space, right? There's a connection that is the relevance. And then there is a notion of, you know, this is matters to me or does not. Yes?
Are these two empirically determined or intuitive?
So these are, in this work, these solve an optimization problem, a discrete optimization problem, okay? So the relevance is basically it's like a two-dimensional optimization, right? A two objective optimization. Right now, I'm just showing it as a single objective under constraint, okay? But the purpose of this part is to show you that the reward itself can be multi-objective. How it's determined, you know, you can define it, you can implement it any way you want. What matters to me is the signature.
Two questions for this work. These objectives are not conflicting because then the problem.
Of course, then it's not a bi-objective problem.
It's not a bi-objective. Okay, and for the earlier work, wanted to ask, but do you also take into account human feedback in the reinforcement? So, but this never came from the astronomers because it's like they never
actually did want. Once we implemented
to.
everything, you know, 3 years down the line, we had the application. They wanted to provide feedback.
Because
and I think to do it properly, one needs more of a multi-arm-banded implementation. Okay. But then we wanted it to be stateful. So in a way, it needs to bring in, you know, the kind of the stateful reinforcement learning and the map together.
But map does it have a human feedback built in? Not sure.
Well, you can more easily, more naturally put it in, right?
Okay.
Because you're basically just revisit the reward function once you pull an arm. And it's more of an online deployment right away. It's not like you're training and having your policy set in stone and then you deploy it, right? So you can more naturally have human feedback in there, right? I still haven't figured out how to bring these together, honestly. Yeah. So there are different ways of computing diversity. The notion of quality. Okay. So if what you're computing is the quality of a set of reviews, okay. For instance, line 2, right, gives you a notion of diversity of the reviews. Okay, so there's more than one way. You can plug in a bunch of things in there, but it's not the most important thing here. So the MDP again is a set of states, a single operation or action, but then it gets instantiated depending on what you give it as input, whether it's items or reviews, right? Whether you're looking for similarity in the review text or dissimilarity makes it another operator, okay? And so on and so forth. We'll see in our hands-on what we have here. Transition probabilities and reward based on relevance and quality, okay? So this is what our MDP is.
Why diversity is important here?
Because, you know, when you're looking at reviews, sometimes you're interested in having people who liked it and people who didn't like it, right? Or diversity of topics. Like, for instance, in hotels, right? You know, some reviews are going to be talking about the cleanliness of a room, and others are going to be talking about whether the bed is comfortable or not.
So we are talking here about diversity of topics, not diversity of labels, right? Like negative, positive reviews, right?
Yes, diversity of topics, not of opinion. Yeah. But you can define it as diversity of opinion. Okay. Think of it as
But typically, if the reviews are honest or somehow, they should be similar, right? I mean, if a hotel is good, the majority should say yes, right? So here the diversity of labels does not make sense.
Depends, right? The distribution of reviews, right? It's not, depends. Sometimes it's polarizing, right?
Okay.
What's the name of that movie? 50 Shades of Grey. It's like super polarizing movie, right? Okay. Now you're smiling. All right. So what's our exploration problem here, right? We're looking to learn a policy that maximizes a discounted utility over time, okay? Discounted is important. Don't forget, right? This is your discount factor, right? This is gamma, right? Is that a gamma? Yeah. I keep mixing them up. Oh my God. Okay. So basically the sum of utilities of applying Explore to either reviews or items or products. So this is what we're optimizing, all right? And utility is based on some similarity between items, but you're going to see how this is actually implemented. But what I wanted to really focus on here, and only 1 minute break, is this notion of multi-reward, or what is called a reward machine. So far, the rewards that we looked at are what? Weighted linear combinations of some dimensions of interest for a particular application, right? Now, what we have here is a reward function that is called a reward machine. It's itself an MDP. How interesting. So what is a reward machine? It basically will encapsulate a bunch of things, okay? Let me explain these to you. When you are dealing with a real application, because my former student had already transitioned to Amazon, and initially when we started, I was like, yeah, great, we have this explore operation and it can do everything, And he's like, yeah, but in Amazon does not allow you to go from one reviewer's review to all its reviews, to all his or her reviews, right? They don't want to do that, right? Okay, because they don't want to enable that to people who do a reviewer population analysis. They don't want Amazon data, right, to be used for those purposes. They don't want people to be characterizing the reviewer population. Okay, so that's forbidden, meaning that there are some transitions that should yield a zero reward. And omega in reward machines is a bunch of application-dependent rules, domain rules, if-then else's, okay? So there are there are basically some pathways in the data that yield a zero reward, regardless, okay? And then you've got, I still have my training set. If I find anything in my training set, I'm gonna get some overlap between the newly generated set of things that I'm observing and my training set, okay? So that's one type of reward. It's like familiarity reward. That's how it's implemented here, okay? Otherwise, I'm just letting my agent find things that are somewhat relevant and of good quality, okay? So this is what the reward is. And the reward itself is a composite algorithm in a way, right? The reward is a reasoning, right? It's not just kind of a single value that's assigned to an action. Okay, so reward machine is a concept that was included, and I should have put the reference there, kind of an interesting Europe's paper from a few years back. So I encourage you to look at it, and it's really represented as an MDP itself, but bottom line, you can put in pretty much everything. There's a reasoning or your reward, and what's good is that it simplifies your state space, your state transition space, right? Basically, you're throwing some of the work, right, of reasoning over your state space into your reward function. Okay. And basically, in this work, what but what Beruz and Aurélien did, they built on top of DQN, deep Q learning, and they use why? Because DQN has something called the replay buffer, where you can store intermediate solutions. And why does it matter to us? It's because we have a bi-objective problem, and we want to, in the training, right, we want to keep all the non-dominated answers. Is everybody familiar with Pareto and non-dominated answers? Okay, if we have two objectives, okay, I saw two hands. We have two objectives, right? We're maximizing both of them, let's to simplify. The point that's up there, right, it's called the zenith point. It's like the best point ever, right? Because it optimizes everything, both dimensions. But in general, there's a Pareto front, right? That defines all the answers that are best either on one dimension or another, okay? Those answers are non-dominated, right? None of them is better than the other. So this is what our buffer is going to contain here. It's kind of cool because you're interjecting the training of an agent, right, with these, what they're calling, experiences, basically. And we're putting this into this replay buffer so we can then reason over all the non-dominated answers. Make sense? Okay, so it's simply saying that it's not just a single answer that yields the best reward, but you've got like a bunch of non-dominated answers, and then you can apply any sort of Pareto navigation to determine what is the best answer. That's really the main thing I wanted to say about this one. There's a little bit more there. And there are some experiments which are absolutely great on Amazon and AMDB. I actually don't want to go into the details of these experiments. I think you should read the paper. And before that, yeah. Okay, so just a summary of this, it's this multi-reward adaptation of DQN. And yeah, user feedback could be incorporated with BAB. And then there is the question of using LLMs, but we're going to do that in the hands-on. Thank you very much for your attention.
Thank you very much.
Great.
Just very simple, single note. Thank you very much. Sihem, do you have any question for her? No? The follow-up session may be hands-on. For the tour yesterday, forgotten to be mentioned that the reason that this building was built as such with mud and grass on top of it is for bioclimatic reasons. Extreme heat, you see how it is. Global warming is, of course, an issue everywhere nowadays. And the reason was that it had to be buried underneath the soil, and then you have no windows. And because of that, you have to bring natural sunlight in the building. That's why they built this cone that follows the sun, and that brings in sunlight to all floors. So it's kind of like the one justifies the next thing. The main reason is actually climatic reasons. And the second thing was to build it like the Aronas, which is the mountain behind us. Whether or not future buildings will be built buried underneath the soil, the question to be seen.
And if they will incorporate any reinforcement learning to decide, how to orient this thing is another thing. Yeah.
Yes, and do not forget the sign sheet outside, because for the certificates we'll need your signature on all pieces. And if you have private work to do, remember that you can make a card and go inside the library. Okay, that's a third announcement. Thank you. And we have to throw in a few like statistic. We have to show at some point, but not at this point.
Kind of like
Yeah.
last part.
We will do it after.
Okay. That's right.
So was it hot or cold? We increased the temperature because we thought it was cold, but it's make it a little cooler, okay? If you feel cold, then I'll go.
of your work yesterday?
Yeah.
For me, I taken up and then I worked till 11 and I was. And today I wake up at 5 and continue working. Do you have anything to do with the weather meeting? I have my meeting today at 6, so I have to prepare something new. Yeah, but I have an experiment that has some errors. That in the system. And your friend did come today here also. Okay, it's a nice way to attend the summer school to attend. Are the things installed, or do you want me to help you in? If not, I am very. And Olam, I did Olam work. Okay, that's cool because I installed it and after installing, I opened nothing.
No, I think it worked. I mean, I got the files that they need or something like that, so let's see.
No, I hope it's. I think it's working.
I mean, they said this file had to be eliminated and there, so.
That's not what you prepared yesterday. Yeah, that's because I was not in the look, he forwarded the email now. This one I didn't have. It's too early.
Well, but it wasn't just a typo or something. You weren't there.
Yeah, I were not there. And he was, oh, it's a mistake. I was like, okay, let's fix this mistake. Otherwise, I don't fix that. I don't have anything to discuss with vice president. So I'm trying to get some now,
Okay. But I'm surprised you're working on this and also.
Multitask. Yeah, I am. I told you about the two masters, so
Yes,
I don't know. I mean, I do that. It's not healthy. I don't recommend it because you will burn out at some point. But there is no choice. Otherwise, I don't want to cancel because I canceled it last week because I have another semester. Also, I felt it's too much to cancel 2 meetings. So I was like, okay, let's prepare some basic thing and discuss. Did you pick the contact for the master?
no, not really, but no. They have to assign the. Okay. We have to. Also, there's one for this. Yeah, we're supposed to give them the advisors a week ago, and we haven't received anything. So,
but you don't choose them; you are assigned to them.
Depending on the
But you can, of course, chat with someone and agree on some topic with some supervisor. No, I mean, because you have to pick someone you like or supervisor issues. Yes, it can make your life either easier or. I mean, yeah, but for you, it's limited time, like 4 months. But for the PhD, 3 years, too much to have it. Choose your bit. At the beginning, no. And then I changed it because I had experience. So I'm telling you from experience. Already someone working supervisor. It's suggesting you. No, it's so you will enjoy more because it's something you want to work in. That's good. But you don't have any group members. It's individual. And I'm working with you. Okay. You should train yourself for this team working stuff. I know responsibility. Yeah, I know this. We will end up doing everything yourself. So same as you are alone. I guess I have similar status in one of the way I did it. I just do the work. At least if the person is nice, I need it's coming from me. If they are not bothering you, that you doing your work, that's fine. And then I will go to I have one teammate, but nothing. No, I'm good. Okay. We take something from him and we are improving it. So, yeah, this is his contribution. So, the thing that he already did.
Yeah, no, it's just the two about another table that we published on Amer-Yahia that we are working on. So yeah, it's super message.
So you are working on
No, not me, but we are in the same lab.
okay. And what
I work on data profiling, so we extract the data, we provide we are still artillery implementation, so feeding these use.
Most of the time the project especially it's like a real company, so sometimes they are getting negative values for time. It's very unrealistic things. So I know how much this is. But do you have any complications?
Yeah. I published it here.
That's why you are here. Recommended values. I work on an okay. We are in biological review of that, and now in our subject for unusual communication. But on that I remember the second project this is very I'm working very much. And you are in training, but oh, okay. Much preparation. Actually, I don't have anyone from my university here. I think they have research group like and my collaborators are not from the research group, are outside. So they are online. This is weird.
Figure it out. All right, let's see. We can try it out. Oh yeah, I need to project out my computer. Where is it? Where is Dimitri? Did you manage to install the things? Yay.
Yeah.
Okay. So you followed the installation instructions. So you've got your Anaconda, you've got your Olama, you generated your API key.
Yes.
Yeah, please don't use the one that's in there because it's limited. And then I just need to figure out how to project out this thing.
Yes,
My
I
own
will do it
computer.
right
So I
now.
show you the code and we
Yes,
just
so
quickly walk through it. So you
Uh,
can see that,
we have to here.
okay. In
Only we have to do
I
one.
don't have this.
Then hold on.
Yeah.
So it's
So what? So yeah, so there are these two variants, right? I mean, in one case, we're training an RL agent. And in the other case, we're instantiating a graph with LangGraph. And, oh, I should have a couple slides that show blah, blah, blah. Oh yeah, good. So in the case of LangGraph, in the code, we're going to go through it quickly. The code, the actual code here is just to show you the prompt to the supervisor or the orchestrator is this one.
it's supposed to be here.
So the task is to find 10 target items. The items are defined with their IDs. The IDs range from 1 to, I mean, there's about 4,000. The target set is not provided. We need to find it. We are receiving a history of previously retrieved items, which is global file, right? That previous agents are generating, and we are to detect a microphone.
It's fine. It will recover. Just have to now.
And what the supervisor is instructed with is not told which agent to trigger. It's only told to find the next agent to maximize the reward, and also to not choose agents that do not provide a positive reward. So that's in the context of the supervisor orchestrator. So the structure that is defined in the code, right, for the supervisor is, oh no, it's not, you're not seeing it.
Yeah, because
Because we just switched.
laptop HDMI maybe. No way to present it on that one, right?
I would have to go online to the drive.
This is maybe.
Yeah.
Does anybody have a dongle? HDMI one? Because this one doesn't seem to work. Oh, there's also USB. Hold on. Okay, hold on.
Okay.
Okay, we got it. Thank you. Okay, perfect. And then there is one more thing with the Zoom.
Oh, yeah.
I will.
Oh, you want me to go on the Zoom link?
I think you can start presenting, and then I will. Yes, can you go to the Zoom link? But you don't know the URL, right? I will send it by email right now.
Who did not manage to install whatever is supposed to be installed?
I will send it by email, and please
What?
click on it.
Who else? Two?
What do we need to install?
Oh,
You're ready for the second part of the talk? Hands-on. You already received the instructions by email yesterday night. A few things to install for Llama, LangChain, as far as I saw.
Yeah.
And yeah,
and,
share screen.
yeah. All right.
Steve?
So, sorry, all.
You have to say share screen.
I did, right? Share screen.
We stop the share screen sharing from here.
Oh, okay.
Stop share. Okay, try again.
Yeah, it's good. I'm gonna share. Share screen. Okay. And this goes away.
Perfect.
And this is the
So-
drive.
Okay.
And this is the thing.
Check your junk. It's something on the Okay.
Yes, sir. Yes. Yes.
Okay, then can you forward?
What
Can
do
you forward it to him? Thank you.
which one?
No, somebody didn't get the email.
Okay.
Um,
For the email, if you can ask Nicholas, who hasn't received it actually, the email. You?
He forwarded already.
Already. Okay, we are ready. Okay.
Okay, so we have two options. We have training an RL agent, and we have instantiating a LangGraph. And this is how it looks like. The LangGraph. It has 1, 2, 3, 4, 5, 6 agents, 6 tools in this case. Like it's the simplest form of agent. The only communication that's allowed is between an agent and the
Yes, we are seeing it. Don't.
an agent and the supervisor. Okay, so they don't talk to each other. Okay, the supervisor is instructed to find 10 items out of a collection of items, 10 items of interest, and it is supposed to decide which of these agents to invoke. Okay, and the order in which they are invoked, right? To find the items of interest. It starts from any point in the space, and we're going to look into the code, and then it decides in what order to invoke these. All right, so that's for the agentic LangGraph LangChain. For the RL, right, the reinforcement learning, it has a reward function that is familiarity with the target set. Okay, and it's going to train your agent, and we're going to look at the two. Try to make the two work. Okay.
Okay.
Okay, so the people online didn't hear anything.
Yeah. Now they see your face also and your microphone.
Okay, so are the people who did not manage to install it able to install it? Are they in the process of following the instructions? Did you download it and then did run servo llama? Or just like use whatever interface they have to launch it? You don't have to go into a terminal window. Oh, wonderful. Okay, so you can open your Jupyter. Are you following the instructions? Are you doing what I'm doing, or? Okay, I'm gonna start from the beginning. Okay. Do you all have access to the readme _install file? All right. As I said, we're going to be looking at these two things, two variants. Did you all follow the instructions for installing Anaconda? Did you make sure that you also pip install all of these things and pip install NumPy? All right. Can you?
Has anybody not finished this process yet? Let's see.
We have the two identified individuals who haven't are working on it. The non-identified ones may be working on it. Yes, yes, agreed. You're totally right. See, some people tried it and others haven't. Okay, did you all install Olama? Are you all able to launch your Olama, little Olama thing with the Olama that should appear here and I don't have it? Okay, so this is an environment where you can load any language, a number of language models. Okay, we're going to be using Llama 3.1.
So it's an open, you can download open source models, and like you don't use a ChatGPT API to run them on ChatGPT. You download them on your own computer. If it has GPUs, it exploits the M processor, for instance, works very well. For those of you with Mac, there is also LM Studio. LM Studio is a graphical user interface where you can download the Olama models on your computer. Very powerful environment for building local applications with the LLMs.
Mm-hmm. So for instance, if you want to use Llama 3.1, you just launch Olama, you pull Llama 3.1.
By Meta. Llama are the Meta models. Yes. Qwen has also by Alibaba.
Olama is not by Meta.
Olama is just a tool to download the models. It's just a tool, but the models are trained, and you have different models. You have 8 billion parameter models. You have there's even a
70 billion,
billion parameter model. You cannot run that on your computer. It's too big. But
to check if your Olama is running, you just run Olama ls, and like mine is running, right? 3.1.
And then you can build with Python like bridges and connect it to your apps if you want.
Mm-hmm. Are we all set on this? Okay. By the way, if you want to use a different model, this is what you should be doing. You should like go and pull another model, and we should change the line of code in the code that I'm going to be showing to you. But the model you should be using here to be able to use tools, the different agents, is a model that should be annotated with tools. Okay, not all of them are annotated with tools.
So the large language model here, Llama, will be used as an agent neural sample in the reinforcement learning.
In the agentic variant, yes. All right, so we've got our Anaconda environment, we've got our Olama. We also want to create an API, generate an API key. Very important, don't use the one that's in the code. It's not gonna scale, you're too many.
So just as a reminder, Langsmith is for what?
Langsmith is the environment in which that monitors LangGraph, LangChain.
Okay.
Okay.
And LangChain is just to
define the
agentic workflow.
That's right. And LangGraph is to represent it as a graph, right? And constrain the edges in the graph. We're going to look at it. And LangFlow is to visualize it.
And just a question for the Llama, you cannot use different models because at every given time point, Llama only loads one model.
Yeah,
memory.
but to use a different model, there is a place in the code to say, I'm going to be pulling a different model and choosing it. But right now, if we're all using Llama 3.1, let's stick to Llama 3.1. Okay, now I'm going, and then, so this is the install instructions. The identified individuals who did not manage to install, if they're not able to install, they should pair up with somebody who has installed it so they can look at it somewhere on some computer, because mine may not work. All right, so now we're going to go to README run. the file in the drive. Once we have gone through the steps of readme install, we're going to the readme run. And we're going to be doing first the RL agent code. And then we're going to go through the agentic variant. And they're doing more or less the same thing.
So can you explain also Jupyter for those who...
Yeah, I'm going to open it up if it works. If it doesn't, then I'm in trouble. Yeah. Yes. Okay. So can you all launch, I mean, those who can, whatever, Jupyter Notebook, follow the, what is it? README run instructions.
You could have continued on the terminal, but it's just easier here, right? That's
Yeah.
the point.
Yeah. Are you all here where I am? Did you make it here? Who did not make it here? Who doesn't care? Okay. If you're not here, we can wait for you. Hey, I've got my companion here. He's checking. You better put the right, you better put the right display. All right, folks. No, I mean, really, I mean, it's, if you want to at least try it out, this is very simple. It's like an oversimplified piece of code. So you can just, you get a chance to try it out. So if it doesn't work out, just let me know and we can look through it. Okay. I'm going to open the RL agent code. I'm going to walk through the RL agent code. Okay. Okay. Did you find it? Did you download, where is it? EDBT school workshop. Yeah, you open it up. It has two subdirectories. One is the RL agent, not two, but more than two. But one is data, one is models, should be empty. Data is not empty. One is RL, one is RL agent, and LangGraph.
So the zip file is the data, right? Or not? The zip file has everything.
It has this. When you unzip it, you find this. Okay? So we have the code for the RL agent. Do we? I'm going to run it cell by cell. You can do the same thing on your machine for those who manage to do the same thing. Are there people online who want access to this thing that maybe?
They see what you're doing now.
Oh.
And they also listen to your microphone.
Well, I'm going to send them, maybe on the chat, I can send them this thing and they can download it.
I think they already received the email.
Okay.
Yeah. Because
Well,
they are...
I put it on the chat in case.
Yeah.
Okay, cool. So there are 15 people who are viewing the README run. Fewer who are viewing the install already. Okay, folks, let's look into a little bit into this code, okay? Should be easy. We're going to look at it and then I'm going to come around and see if I can help. All right? Okay, so this is the RL one, okay? So what are we doing here? Actually, you know what? I'm going to start with the other one because the other one is kind of more maybe newer for people. And then RL is going to appear more as a simpler. So for the other one to work, listen up, for the other one to work, we're going to open a Jupyter Notebook and we're going to go into the LangGraph subdirectory. Okay, I'm going to open it up. But you make sure for it to work to launch Olama, right? And once again, to replace the API key in the second cell. I'm going to show you where with your own key, the one that I hope that you've generated using the instructions that were given previously. So we're going here and we're going to open LangGraph. Okay. And all right, so what is this doing? This is basically just getting some libraries, that we need. Lots of things about the graph, the start and end, basically the graph structure of LangGraph, the tools and messages, and telling it that it's going to be using Olama. Okay, so we've already configured it. And now we're going to go into the second cell. What is doing here? This is what's setting the API key. This is the line where you should put your API key, the one you generated following the instructions that are in the README install. Okay, now what are we doing in this cell? We're going to read data and set some parameters. So let me here explain. The data set is electronics. There are different target sets that we can set up here. Right now, in the current version of the code, it says homogeneous items. This is a set. This is a target sets that we're looking for. Okay, but we may be looking for others. If I go to the data directory, there are many targets that I may be looking for. Okay, I'm just saying that I'm right now looking for the homogeneous ones, but we can instruct the orchestrator to find different types of targets. Okay. Similarly, for the RL agent, we can train it to find different ones. We end up with different policies. Okay.
Their similarities are close.
The homogeneous ones, yeah, they're very similar to each other. Okay. What else? Again, the data environment, the data directory is the one that contains the data. The reviews are, they're there. They're of type review. The items are of type items. And then how do I start? Right? I'm going to start randomly in the space. Right? Basically, I'm just mimicking a user who's just going to start on Amazon, on anywhere, and I want my orchestrator to generate a series of calls to those specialized agents to find the target set. Got it? Then the expected output is okay. Yeah, there is a set that is my target set. That's the one I'm looking for. And it's going to come further down. The set of actions, which are the specialized agents, are these. So I'm telling my orchestrator that it's going to have the members that go into that it has access to are any of these. Okay. It doesn't matter. And then I'm building a history. This is important. This is memory. Okay. I'm building a history file that's a global file that's going to be passed along calls to individual agents. My history file is going to have the agent name, the retrieved items that I got from before, the retrieved items that happen to be in the target set, the number of retrieved items in the target, the similarity between retrieved items and the target. This is context I'm giving to my agents.
And this is done with pandas in your case?
Yeah.
And if you wanted more performance, you could have used polars, for instance, right? Which is distributed.
Listen to the expert. Thank you very much. Yeah. Okay.
So, but your data set is big, but not like huge, right? It's so you would need more scalable data frame processing with polar.
Absolutely. And the reason it's smaller here is so that it runs.
Data with Blink maybe.
Okay. Mm-hmm. Absolutely. All right. So these are the individual tools or agents, right? That are defined as similarity by attribute, gets 10 objects based on similarity of the attributes that describe that object. Okay, objects are either items or reviews. Then similarity by tag, similarity by summary. Okay, so these are the different, I'm defining them, right? I'm telling the system, these are the things that you have access to. And then I'm going to tell it how to instantiate the graph and what governs the end, the start and end, and the relationship between them. I'm not going to tell it at all in what order to call what. Okay, I'm just hoping that the agent, the LLM, has been trained. It has so much knowledge that it knows, you know, which one of these agents to call, right? Somehow it's going to figure out, given the instruction that I'm giving it, which one of these agents to call. La 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 la. So these are all the different agents. And then, how am I calculating the reward? Okay, this is not an RL agent. It hasn't been trained on this particular task. So it is more of a forward look. It's basically just, okay, you have some history, you have been trained on the web, on data on the web as an orchestrator, and you have access to all these tools, and you need to determine which one to call next based on this reward. Okay, so basically the reward is based on the notion of relevance, remember? And it puts the reward information inside a file because it's also information that we're going to pass along. You can see that I'm like skipping over stuff. Huh? I want to show you how it runs. Okay, so the actions are defined as tools. Here we go. Now we have our prompting. Okay, so the prompting is you are a supervisor overseeing this task and you have access to these members, which was defined earlier as being members are the different tools that is given to it. Your task is to do this and that and to come up with the highest reward according to some reward mechanism that I just defined for you. You haven't been trained for it. And now figure it out. Okay, so you're going to get your prompt. There is some history. Okay, and you're allowed to ask the next agent. And you're going to be using Llama 3.1. Okay. And now, what is this doing? I think this is telling, okay, you know, something about how to manage history. You know, was there history before or not? And then I don't know what. Yeah, figure out what the next agent. Oh yeah, because I also wanted to tell me at some point, I'm calling this agent and I'm telling you why I'm calling this agent. You're going to see the trace is going to look like that. Then I'm launching it, okay? And that's it. Well, not that's it. There is a little bit more. When should I stop, basically? How should I like call and when should I stop, right? Okay, something about message management. It's very basic. I think this was copied exactly verbatim from what it was. And now I'm going to define my graph, right? This is our length graph. If you're using only length chain, you stop here. You're just like, okay, go and run it and then eventually give me some result. Now I'm going to use length graph because I want to render, right, how these different nodes, what is the workflow, okay? So I'm going to define my graph, the interactions, the edges, right? And as I said earlier, my graph is going to impose that tools or the specialized agents are not going to talk to each other. They only talk through the supervisor. So it's happening here. Define the graph, it's state graph, supervisor calls our model, and then the members, and then whether it should continue or not. And I always start with the supervisor. Okay, and I'm compiling my graph. Then there are some parameters of recursion limits and how often I should be calling the different things.
Do you need to go through all the steps every time, or you
Sure.
just...
No. I mean, I can just run everything. I think I know why I have an error. I think it's because my history is not empty. Okay, so you should have an empty history if you haven't run it before. And I'm going to go in and see how to get rid of my... Good. Who did it work for? New window. I think it's because I have a... yeah.
I'm trying to understand the big picture, actually, but I'm struggling. my understanding is that there are like 4 or 5 agents, and
Yeah.
the main agent,
I'm going to start again. Yeah, I'm listening. Huh?
and the main agent task is to pick one of them. Okay.
So the orchestrator is told this. Okay, that's in the code. Then the orchestrator is going to decide which of these to call in what order. That's it.
Okay. And each one of these agents, it will be trained.
No training. These are just
This code.
these are either code that you write in your system, or they're themselves language models that are prompted to do some similarity, or that are prompted to find other reviews that have a similar sentiment or a different sentiment.
But the supervisor trained as a reinforcement learning agent.
No, the supervisor is another agent. There is no training here. It's all inference. For this variant, there's no training.
No reinforcement, no planning.
There is planning. Wait, so I'm going to relaunch the thing. I'll show you the code.
And connect that with the reinforcement learning.
Reinforcement learning, we're going to go back to it, right? Reinforcement learning is the one where I am going to be training an agent, just like what I explained.
Different, separate than this.
It's separate. It's two different implementations. One is a LangGraph agentic environment, and one is reinforcement learning that we are training ourselves. What I just described, this thing, is a step-by-step, which I'm going to go through again step-by-step, so you get to see it, is a step-by-step definition of the environment, meaning the graph, that will make use of a language model as an orchestrator by giving it the right prompt, which is somewhere, this is the prompt up here, okay? There's no training. It's just, it's been trained by other people. It's Llama 3.1. I'm telling it, this is your job. All right?
But I give it the step to get the job done.
I give it just the tools. I don't give it the individual steps. I tell it, you have access to these members. Members are similarity by tag, similarity by sentiment, blah, blah, blah. Now figure out how to orchestrate them. That's it. Okay?
All agents are language models here.
Language model, actually in this code, I'm not sure all of them are language models. It's working, okay. I'm not sure all of them are language models. They're actually, the orchestrator is a language model, right? And then I'm giving it access to code that I wrote, but there can be any other language model.
And as you showed, there is actually their body of each agent, let's say. That's it. Which is with this reward function internally. So she showed 6 different
Yes.
functions. So these are the kind of internal steps that need to be figured out by the orchestrator.
So the supervisor, right, is going to make the following decisions, right? It's going to, it starts randomly from the space, right? It starts randomly from 10 products, right? That it pulls out of the 4,000 products, and it selects one, and then it applies similarity by tag. I don't know what this first step is, but anyways, once it has a set, so this is the input, 10 products, okay? It's going to apply similarity by tag to these products, given an input ID selected, 658, and out of this, this first call is going to find 10 other items in the set of all products available, 10 other items that are similar, the most similar by tag. Okay, so the supervisor decided to start with a similarity by tag, right? Decided to do that based on the fact that it was told your reward is to find items in your input set. Okay. Then it applies the similarity by tag, and it tells you similarity by tag was called first, and it retrieved 10 items with a similarity of this, which is minimum similarity to the input item. And the goal was to maximize the number of items in the target set that are not already found. Okay. Therefore, we need to choose an agent that will retrieve new items that are likely to be in the target set, right? So this is the language model that's telling you that. Comparing the history provided, because we're giving a global file that's telling it, there is not much history here to start with, but you know, if we choose another agent with a similarity, blah, 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 it would be beneficial. Apparently, so the next function that it chooses to call is similarity by text, which is basically just looking at the two reviews, the embeddings of the two reviews, and it's looking at their similarity. It decided to choose that one. And so on and so forth, and it keeps telling you stuff, similarity by text, yeah, and then another apparently similarity by text. This is mine. I don't know what you got. Yeah.
Determination is by threshold, or what is, or you showed it earlier.
Did anyone figure out what the termination is? Yes, go ahead.
I can get the history file, and also the output at the end is only the last block that you have as well in your explanation of your data.
Well, I seem to have a number of them, right, myself? Can we look at the history? Maybe it gets overridden.
This file is not generated.
Can you write into that directory just in the basic questions? Make sure the, you know. Who does not have a history file? Okay, we have two who don't have a history file. Who has a history file? A bunch do. Okay, we'll figure out the history. We have a first problem that is history. Let me go through the RL version. So at least we've covered these two grounds, and then we can go around and see what's going on. The RL agent. All right, so the RL agent is basically going to actually, you know, generate the RL agent, right? Train the policy. So here, yeah, so the library is a PFRL, okay, that we're importing. Okay. Okay, so that's the one that I showed you earlier, right? The Explorer that has different implementations. Again, I'm setting the same target variance. By the way, the assignment is that maybe you can train a couple agents, one that has homogeneous items, one has heterogeneous items, and show how it works, but then you have to be able to generate a history file and stuff. So, okay. Then what are we doing here? Same thing here, right? We're basically just determining the targets and a bunch of parameters, right? There is so one hot encoding of so the encoding of each item in the space that we have here. The state for the RL agent is defined as being the encodings of all the elements it has, all the items that it generated, plus the item that's going to be picked for the next operation, right? So you've got the set of K items that we're generating, which is 10, just like we're doing for the non-RL version, and plus 1, which is the item that's going to be used for the next invocation. Number of episodes, made it very small, so you know it actually terminates. The number of iterations.
The number of episodes.
Yeah, but it's
80. It's fixed.
Yeah.
Condition.
Yeah, but it generally over 1,000. Yeah. It is a stopping condition. Yeah, it's generally more like 1,500 to 2,000. The model name, okay, whatever. Initializing the environment. Okay, so it's the gym environment here. All sorts of things about the decay factor that I mentioned earlier. And it's, in fact, it's using epsilon greedy in this implementation with an exponential decay. And then the agent, the replay buffer, as I said earlier, right? So that we're putting the capacity of the replay buffer. We don't have to put all the answers there. We're using the Atom optimizer here to optimize, to do the bi-objective optimization. And then the DQN, okay? And then, yeah, just some stuff to make it happen. And we're logging some of the model names. And now I'm going to launch the training of the agent, okay? With all the variables that I had set up from earlier. And what this should do, as I'm saying in the drive, I think I put it in there, DBT, the training of the RL agent should where did I put that? It's here, right? I don't know where it is. I actually did put what the training of the RL agent should be generating. It actually generates, here. It creates a directory depending on the model name. So we've chosen to find homogeneous items. So your model is going to be called something. And so we're going to go into workshop models and look at this. Yeah, so it is creating my model, my electronics homogeneous items model. I think it's still working. So this model, right, is the one that I trained from scratch. Okay, that's my RL policy versus my LangGraph thing that is doing this. Okay, I think I've gone through more or less what it's doing, and now I'm gonna come around and see what's going on and why stuff are working or not working. Okay. Of course, those of you who could visualize this stuff, either with LangFlow or with anything that's in this environment, Jupyter environment, it would be nice to look a little bit at it. Okay. By the way, there is more. There is, I know there's a question in the back. Okay, so we've got the data, we've got this. What's in the RL? I just want to check, I forgot. Yeah, this is just the stuff, the utilities and... Okay, for now, let me go around and question. Yes, in the back? Can't hear anything.
When we are in the state spaces for RL, we are adding 5 along with the one item size. What is that additional 5 for?
Yeah, it's the additional features of that state. I don't know. I don't know exactly because I know exactly where it is in the code. It's basically 5 plus K plus 1, huh? Yeah. This thing, right? I don't know. I need to find out. I think it's something that we should be able to find here.
So if they want to follow the steps, they have to go into the file system, right? Yeah.
The README.
The training file system.
Yeah, I'm gonna try and find it. For me, it's still running. So it's RL agent. Where am I? RL. And so history is the one, no, the history, let me just check first history if it's still there. No. So this is the RL agent, the agent, the LangGraph one. The one that is models, right? The RL ones is this one.
This is the log file.
exactly. And here,
Can you show it?
yeah, there is a directory that gets created when your RL agent, there is directory that gets created when your RL agent is trained. And here, you can find the steps,
Right.
the training steps, that has the following schema. The reward step, the reward of the step, the target found. This is what it's writing into this thing. It's training it and it's writing into this file, right? This is a training trace of your RL agent. And you can find it in models, and then it creates this directory that has the name of your RL agent. Inside that, there is training, and then there is score.
So the reward goes down gradually as we get there, but
It should stabilize.
it should stabilize at some point.
Mm.
So the first column is supposed to
Wait,
decrease because you're optimizing.
it depends, at the beginning, and also the number of episodes is small.
Yes.
So it's going to be
I think you said 10, right? And then 80 for the regular run.
80 for a regular run, yeah.
But now you're doing the test, I think. It's 10 or 80.
So 80 episodes, yeah. Wait, and there is a number of iterations inside. Give me 1 second. Okay, and then I have my target model. Oh. So it is still updating it. 1141. No, it's done, I think, in my case. It's not going to be great because it's only 80 episodes. By the way, once you have your model, you can run the inference, right, of the RL model, right? And for those of you who can run it's under the directory best, I think. ls minus la. Homogeneous. So the name of your model directory, inside there is best, right? And your target model is the one that you're finding. And in fact, we should be able to run the inference and compare the items that it found versus the ones that are found by the agents, the LangGraph agent. I want to see that if it's possible. Did you manage the history thing?
Well, now I rerun because some people followed the document and first executed the RL agent and then
It's okay.
I did the opposite. But I suppose that this won't matter.
Doesn't matter. It's two different pieces of code and they're writing into different directories. But did your RL? Okay, but your RL agent is able to write into your directory, so you don't have a problem. So what's going on with your history file?
It's a model directory inside the electronics.
Sure.
And then
Yeah.
3.pt.
Okay, and then you can look at the one that is best model and see if you can run it.
And then when I run the LangGraph,
Yeah.
I can see on the website of LangChain that I got an input and an output. The response of the model. No.
Because the national report is supposed to create the history file. Nobody has to follow.
Yeah, but they delete your history file before.
Yeah, just
Okay.
maybe there was connection.
So Jianyang, did you manage to run your? Okay. Yes, sorry.
What is it? Run the inference target model. I don't know what the data is expected into the
Yeah. How are we going to run the inference for the RL agent? That's the question. Yeah. So we've got our agent, and then now we need to run it on the data. So you're getting a .pt, right, in terms of best model. And that one, if you launch it, does it do anything? The answer is no. Probably, yeah.
But it seems that many have some, I mean, some have compilation problems, maybe from people that done it. What are, I mean, with library inclusion? What can be possible causes here?
What's the error?
Like at the import library, they don't get it. It's probably that they didn't install the necessary toolchains, right?
It's just in the README, there is all of them. If they were installed,
They have to adapt the paths for instance or something.
no, that's
Not there.
just that's for even like the non-qualified version, it's essential.
And no reboot or whatever.
No.
So maybe try to remove more.
Yeah, somebody knows.
Okay. Again,
I'm trying to see if I can run my model in the Anaconda environment.
They're all set. Hi. Just try it.
Did any of you manage to run the model that's generated, to run the inference? The RL model inference, did you manage? I'm trying to run it. Yeah.
Okay, now time to run. And now we should then something okay, just okay. So
Okay, what was the issue?
it's just because the driver should be uploaded like same. For me, I forced myself
Okay, first question. For those of you who managed to run it, did you also manage to change your target set and retrain and run a different occurrence? I hear a no. I'm gonna try and run the model, but it's not working in my case.
Can we also do the command line or? So with one API, or the ODS? Or do they have any software on it?
Everybody was
The same.
no, everything is fine.
Yeah. Yeah, I don't know how. Okay, so, all right, so the open questions. All right. No.
But it will stabilize. It's reinforcement learning. Monitor.
Okay. Let me give you the last slide and then we'll walk our way back. All right. So these are all open questions, at least some of the ones that, there's one question that has to do with coming up with a reference architecture, right? Kind of understanding, how to bridge the gap between this AI planning where you did not train an agent properly for a particular task, but where we're using some pre-trained reinforcement learning, which are these agents, the LLMs, right? And relying on their pre-trained knowledge to decide how to do the orchestration. For that, in its more general form, there's a question of, I'm suggesting a task. In the code that we have, the task, breaking down the task into individual subtasks has been done already, right? So the different subtasks are the tools that you have been using. But there is the question of agentic AI task decomposition. Also, even discovery of agents, right? Which is something that, in our case, with giving those agents, right? We're making them readily available to be orchestrated, but there is a question of discovering those agents, all right? Then there is a whole set of questions related to personalization. There is a set of questions that are related to the use of vector databases for memory management and for having stateful agents over which we can ask questions and deal with the states, right, that they have gone through as do kind of a policy management and ask queries over those policies. Open questions on responsible deployment of AI agents, and then finally, evaluation of AI agents. Okay, so let's go back to each one of these. This comes directly for some of the work that someone has been doing. This was this guy. All right, so in terms of reference architecture, right? The most important, so there's kind of a different components to this reference architecture. How they are architected together is another question, but there is the question of, is there an agent marketplace and what constitutes the agent marketplace, right? So in our case here, we used the Llama environment and Llama 3.1 that we're loading in, right? But you can imagine that to formalize this space, right? You would think that one could define sort of an agent marketplace with different abilities, right, of these different agents. There is the question of orchestration, the orchestration layer, then the integration layer that is about, are we integrating external, in particular, enterprise data? The shared memory layer, which in the simple code that you got is a file that just gets everything that was the history file. And a governance layer, okay? Governance is more related to responsible deployment and so on, okay? Now, you can see that the orchestration layer is what is user-facing or application-facing. The memory management layer is all the way at the bottom, right? Which is basically, are we managing memory across different agents? How is it represented? And is it in a database, right? And then there is the agent-to-agent and agent-to-human formalization in a way, right? So right now, in the orchestration that you have seen from before, the agent to human was through a prompt to the orchestrator. And that was the only thing that was interacting with the human, right? But you could imagine having more of a human in the loop, interaction. All right. The task decomposition is something that has been studied quite a bit so far, not necessarily in the context of agentic task decomposition, but in the context of chain of thought, okay? Or tree of thought, which is basically learning how to break down tasks, right? Or at least teaching some agents how to break down tasks into subtasks, right? This is the example of the trip booking. There is the main question here is whether this decomposition is done in a dynamic or a static manner, right? So the task decomposition could be a one-off, right? It's done at the beginning, and then the orchestration and everything is defined afterward. Or it could be that a task only appears as a result of having gone through some inference, right? So these are the two, I guess, the two main questions that can be addressed. As I said, there is some work. There's a piece of work by Wei et al., 2022, that is chain of thought for task decomposition. And so it's generally can be organized into either through user prompting. So the user provides a logic about how to approach a certain problem, and the language model will solve that problem by suggesting the decomposition into tasks, okay? Or by automating it. There is a framework called auto chain of thought that itself is going to basically learn how to decompose a task. And there is tree of thought that is about exploring multiple decompositions in some structured way, where the point is to generate a tree that itself, you can limit the depth of the tree, right? And say that each task will have a certain granularity level. And then the tree itself is usually explored using tree navigation algorithms, depth first or breadth first.
Node is a separate decomposition, so each node is a task.
So each node, well, in fact, at the very bottom are the atomic tasks, right? And then each node itself is a task that can be itself decomposed into subtasks, right? But so it depends, how the training is done, right? Is it done in such a way that you are limiting the granularity of the tasks, right? And is it done in a way where you're instructing it by the ability of the tools that you're using, right? Yeah. The second thing is about agent discovery, right? So right now, the way it's done is very much hard-coded. Like I write my own code. I decide that the agent I'm going to be using are this and that agent, right? But to structure this space, there is a need to have some kind of registry of agents, right? Where we have some metadata, like an agent marketplace, right? Provided by different providers. And then the algorithmic question, right? The agent discovery algorithmic question is how do you match a task requirement, right, to agent capabilities? Okay, right now, these two worlds of task decomposition, right, and agent marketplace discovery are explored separately. But of course, they're not separate, right? The task decomposition should be instructed by the agent marketplace that you have. Okay. Right now, these are really seen as silos, right? So the task decomposition is very much used by people who do tree of thought, okay? And with some requirements, and then how far down should I go in the tree, right? What is the depth of my tree? How do I break down the different requirements of the tasks, right? And how do I learn this decomposition? And whether the decomposition is on the fly, right? Or is it a static thing?
The composition is just for creating the building blocks as you defined statically before, right? The
That's right.
Functions.
Yeah.
So
yeah, but it is
either automatically or somehow you gather it from marketplaces.
Exactly. And now, it should be, but the way it's viewed is that, look at this, right? So I have my task and decompose it, right? With some mechanism. I don't know it doesn't matter. So you see task decomposition in the middle. It gives you a whole workflow of tasks. And then you go off and say agent discovery, right? Which assumes that you have agents that have been exported or made available with their own capabilities. Imagine that what you're doing is you embed, right, the task description, the task requirements into some vector, right? That's one way to do it. You embed the agent marketplace and the agent abilities into another vector, and it becomes a vector comparison of agent discovery. Okay, but in reality, the real problem from an algorithmic viewpoint, an interesting problem, is a dynamic problem of saying that given some agents that appear with their abilities, how do I decompose a task to match the agent abilities, right?
Build your own agent.
Or build your own agent. Okay. I'm not going to go into personalization because I don't think it's time. And it's also kind of a little bit of a high level thing where, in fact, they talk a lot about persona, right? You have a bunch of users and you have some user data and preferences that you can represent as embeddings, okay? And this personalization layer is what could instruct afterward, you know, the agent discovery, for instance. It's just kind of an additional layer. Just I wanted to put it in there. But now, the use of vector databases. Today, the use of vector databases in this space is mainly to enable RAG, okay? Right, for, you know, tuning language models. But I think there is a huge potential in enabling, like in using vector databases for what you can call a conversational memory management. Okay, so what is that? Obviously, these agents, they were designed by themselves and each one of them is able to do a bunch of things. And now we're starting to coordinate between these agents, right? The basic way to coordinate between them and have a little bit of memory, right, is through the file, the global file that you manage to hopefully fill and make and use, right? The history file, okay? So that enables some data transfer, some level of data transfer. It's not very elegant, right? It's just some global file in which we throw in everything. It's like we've done this and we've done that, and these are the rewards that we've received. Okay? But of course, what would be absolutely, what would be even more useful and more structured is to kind of formalize what is it that I throw into this file, right? How do I create embeddings? How to create a vector database, right? What is the level of granularity of the embedding of a memory? What is a memory, really? What am I building, right? And being able to do searches over this, right? Over these different embeddings, okay? There's a lot of work. There is a recent paper at SIGMOD that builds over PACS, you know, which is kind of a data layer for vector enabling vector search, like to do things like nearest neighbor queries, similarity joins, right? All of this is based on looking at, vector similarities, okay? So why does it that even, like, why does it matter, right? To be able to represent the memory, whatever I have implemented so far, in a vector database and like, be able to encode it, right? And do some vector similarities. Does anyone know why that matters? Can you guess? No. Why does it matter to be able to represent memory in these systems or in these orchestration as a bunch of embeddings and then manage that as embeddings and compute similarities and nearest neighbors?
Speed and also number of calls. You can like rank.
One.
If something goes wrong, you can see
Debugging. Two.
You don't need to retrain, so you can dynamically ingest data. In reinforcement learning, you have to retrain. Takes time. This one is more agile to additions, deletions.
Yeah, that's like one of the key things, right? Is that, what you want, because what is going on when we're deploying these agents, right? The LangGraph part, there is no history. I mean, there is, if we have a history, but I mean, like, it's not like we trained models and we have a model, a model that sort of stores the steps and everything, right? We don't. It's an inference process, right? And that inference process is lost if we're not building a memory, right? That inference process is lost. Yeah, there was a question?
No, you wouldn't have to retrain anyway.
because the policy might change.
It may, but there are conditions under which you can make use, right, of what you have retrained eventually if you store it properly, okay? Actually, we have an upcoming VLDB journal paper with a former student of mine where we look at how do you combine policies in under a very simple scenario where the new reward is simply adding up two rewards, okay? So we trained a policy for one reward, we trained a policy for another, right? And what we want is to kind of put them together, yeah.
Isn't that similar to federated learning?
How can I answer this question without opening a rabbit hole?
Similar to what?
Federated learning.
No, federated.
I don't want to talk about this. I want to talk about this. Okay.
Smartphone.
Yeah. So federated learning is about, you're not sharing basically your data. And what you're doing is you're sending model updates, right? And you're learning a model, right? And what you're sending is gradient updates, for instance, right? So that you end up learning a single model that makes use of the data that hasn't been shipped over, okay? It's all about training, right? What we're talking about here is reusability, is to introduce a stateful execution of AI agents to have something that can be called like agent ops, just like ML ops, right? So rather than the difference between these two implementations that we tried out, right? One is training an agent with a given reward function, blah, 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 generating a model.pt or something that for which we still have to run inference, right? And the other one is simply running the inference, right? Because the models have been trained before, right?
If you allow me to also clarify this. So, you can train, if you want to train in distributed fashion, like Google did with their smartphones, they wanted to learn how people write, but people do not want to share what they're writing on their phones. So they keep the local data. This was a 2016 paradigm, quite old. Federated learning is quite old. So Google kind of like allowed each user to train its own thing, ship it over, average it, and then eventually they were getting back the huge model that allows you to know how to write. It's quite old, and this has to do with training. What Sihem presented today with the reinforcement learning and building agents, you can think about it as, ChatGPT currently has in the backstage kind of a agentic processes already. You see it sometimes it's doing RAG, sometimes it's scrolling the web. So this is like one way to do it. The thing with the vector databases is another way to do it. There you have embeddings, and that are kind of stored in a multi-dimensional database like ChromaDB, for instance. Then you have the all nearest neighbor search.
Yeah.
Hierarchical.
Yeah. So imagine having the ability to make these inference that we did with the line graph stateful, right? Basically every one of those steps and everything. So we store whatever outcome we had, like you saw the outcome, right, in text. We store it, right? And then we're able to run queries over that, right? There are local queries, composite queries, relationship queries, historical queries. Here are examples of such queries. What is the current state of an agent, some agent execution, right? That's a local query, right? Have agents A, B, C reached state XYZ? Okay. I mean, basically these become first-class citizens in a database that's like a vector database. Given an agent, find me the closest agents, right? Nearest neighbor search. How many times have agent A, B something? Or what was the state of agent A when agent B was in state Y? Okay. So we're talking now about doing monitoring, right? These people are doing it. They have like this Lang Smith and stuff, but they're doing it, in their own black box tool, right? Now we're talking about, what would it take, right, to represent all these stateless executions as stateful executions and making them manageable the way we know how to do it in databases. Voila. And then a little bit more, just these agents that you tried, the tools with the orchestrator, right? they're basically, they don't have a forward-looking ability. They're really looking at a very greedy, stepwise choice of which tool to invoke, right? Based on what they have learned in the past, okay? And there is a lot of talk about bringing together the reinforcement learning, right? And this agentic stuff. And basically, so basically, introducing a notion of reward, right? So I have a VLDB paper last year, just by myself, because it was like an invited paper, where I talk about, how do you take these line graph agent orchestration, where you're not constraining, the notion of reward is very lightweight. Imagine in an imaginary world where you have pre-trained something, you did, right, with your RL agent, and you build some kind of a transition matrix, right, that gives you potential, like what would be the reward of transitioning from state I to I+1? It's you create a RAG, right, a file, you give it to your LLM, right? That doesn't exist, but imagine just having such an extra information. What would that do? It would introduce reinforcement learning, right, into this agentic space, right? It would introduce the ability to look forward in terms of transitions, right? What's the rewarding mechanism in the agentic world? We still don't know how to do it, okay? So in that paper, you can see some very kind of simple way of doing it, but that's one way. And then finally, I'm not gonna say anything here because it's too late. People talk about a number of things, basically, how can we take what we have been looking into in the fairness and bias space of algorithmic bias, right? So just to give you a high-level picture, algorithms are biased because the input data may be biased, or because the algorithm itself is doing something, or because there's a post-processing, right, that's biasing the outcome. Okay, notion of bias, there's a wide range of notions of bias. The same thing can be overlaid here in the space of agents, where can the bias be, what kind of bias and where can it happen? Is it a bias that is the data bias, a representation bias, right? Is it an evaluation bias? Is it, different types of biases? For instance, representation bias arises due to training data that is not representative. These are questions that haven't been touched upon yet at all, right? This is a table that comes from this paper by this guy, who's basically, actually, this guy is not really a scientist. He's more of he works with a bunch of people, but he's done a bit of a characterization of what at least an interpretation of what reliability, reproducibility, and explainability mean in this space. And then, sorry for not having time. And finally, and this is the very last slide, there is a question of evaluation, how are we evaluating these systems? We kind of know there is a number of things that are quantitative, the API costs, the energy costs, things that can be evaluated, like the use of these AI agents. There are evaluations that are dictated more by data, which is if you have a target set, are you finding that, accuracy measures, which is the top left. But there are other dimensions of evaluation, right, that that appear in this space, such as the user experience, and then also things that have to do with privacy and regulation compliance. With that, I'm just gonna call it a day, and thank you for your attention.
So, okay, so we are almost ready for lunch. I just wanted to also, if you allow me to add one parenthesis also to the vector database part. It fits well, maybe it interests you too. So it will just take for a second. Don't stop. Okay.
Stop share.
Yeah, yeah.